Did you know that if you could travel at the speed of light, time would literally stop for you? That's just one of the mind-blowing concepts we're going to explore in this video, as we take you on a 2.5-hour journey through the most complex ideas in theoretical physics. But here's the twist. We're not just here to blow your mind. We're here to help you relax and fall asleep. As we delve deeper into each concept, our explanations will become more abstract and dreamlike, mirroring the way your thoughts drift as you fall asleep. It's like a lullaby for your inner physicist. Alright, let's dive into Einstein's theory of relativity. It's pretty wild stuff, and it's gonna make your head spin a bit, but in a good way. So, back in 1905, this guy Albert Einstein comes out of nowhere and drops this bomb on the scientific community. He publishes his special theory of relativity. And it's like he flipped a switch and suddenly everything we thought we knew about the universe was turned upside down. Now, here's the thing. When Einstein first came out with this theory, nobody really knew what to make of it. It was just too out there, too weird for most people to wrap their heads around. But Einstein, he was onto something big. He was saying that time isn't this fixed, constant thing that's the same for everyone. Nope. According to Einstein, time actually changes depending on how fast you're moving. I know, it sounds crazy, but stick with me here. Einstein's theory says that if you were to hop on a super-fast spaceship and zoom around the galaxy, time would actually slow down for you compared to someone chilling back on Earth. It's like you'd be living in slow motion while everyone else is going about their normal lives. Now, you might be thinking, come on, that can't be real. But here's the kicker. Scientists have actually tested this out. They've used these incredibly precise atomic clocks and put them on airplanes and satellites. And guess what? The clocks on the moving vehicles actually tick at a different rate than the ones on the ground. It's mind-blowing stuff. But it gets even crazier. You know that GPS in your phone that helps you find the nearest pizza place? Well, it actually has to account for this time dilation effect. If it didn't, your phone would think you were miles away from where you actually are. That's how real and measurable this effect is. So, Einstein's got this special relativity thing figured out, but he doesn't stop there. In 1915, he comes out with his theory of general relativity, and this is where things get really trippy. General relativity says that gravity isn't just some mysterious force pulling things together. Nope. According to Einstein, gravity is actually the curvature of space and time itself. Think about it like this. Imagine space and time as this big fabric, kind of like a trampoline. Now, if you put a heavy object on that trampoline, it's going to create a dip, right? Well, that's kind of what massive objects do to space-time. They create these curves and dips, and other objects follow these curves, which is what we see as gravity. This idea of space-time as a fabric that can bend and stretch, it's not just some cool sci-fi concept. It's actually the foundation for understanding some of the most mind-bending things in our universe. Black holes? They're like extreme dips in the fabric of space-time. Wormholes? They're theoretical tunnels through this fabric. Even the expansion of the universe can be explained using this model. Now, as we keep exploring Einstein's ideas, we're going to see how they connect to some even weirder stuff in quantum mechanics. But before we go there, let's take a moment to appreciate just how revolutionary Einstein's theories were. He completely changed our understanding of the universe, and he did it with nothing but the power of his mind and some crazy math. Einstein's theories have been tested and proven time and time again. Every time we launch a satellite, every time we use GPS, we're seeing relativity in action. It's not just some abstract concept, it's a fundamental part of how our universe works. But here's the really cool thing about Einstein's theories. They're not just about explaining how things work. They open up possibilities for things we haven't even imagined yet. Time travel, wormholes, parallel universes, all of these ideas stem from Einstein's work. He didn't just explain the universe we see. He gave us the tools to imagine universes we can't see. Alright, let's take a quantum leap into the weird and wonderful world of subatomic particles. Just when we thought Einstein had given us all the answers with his mind-bending theories of relativity, along came quantum mechanics to shake things up even more. It's like the universe decided to play a cosmic prank on scientists. And boy, did it deliver. In the early 1900s, physicists started to realize that the laws of physics that work so well for big things like planets and apples don't quite cut it when you zoom into the tiniest scales of reality. It's like trying to use a map of the Earth to navigate your way around a single grain of sand. It just doesn't work. This realization sparked a scientific revolution that would change our understanding of reality forever. Now, this didn't sit well with everyone, especially not with our old pal Einstein. He got into some pretty heated debates with other physicists like Niels Bohr about how the universe really works at its smallest scales. It was like a cosmic boxing match, with Einstein in one corner defending his classical view of physics, and Bohr in the other, championing this new, strange quantum world. So, what's so weird about quantum mechanics? Well, buckle up, because it's about to get trippy. One of the key ideas in quantum mechanics is something called superposition. Basically, it says that particles can be in multiple places at once until you look at them. It's like Schrödinger's cat, but instead of a cat in a box, it's electrons doing the quantum dance. Now, you might be thinking, that sounds like some crazy theory that scientists came up with after one too many late nights in the lab. But here's the kicker. They've actually seen this happen in real experiments. Scientists have observed something called quantum dots exhibiting superposition, proving that particles really can be in multiple places at the same time until an observation collapses their wave function into a single state. It's like the particles are playing a cosmic game of freeze tag, and our observation is the "it" that freezes them in place. But wait, it gets even weirder. Quantum mechanics also tells us about something called entanglement. This is where particles can be connected across huge distances instantly. Einstein famously called this spooky action at a distance, and he wasn't a fan. He thought it was just too bizarre to be true. But as it turns out, Einstein was wrong on this one. Entanglement is real, and it's one of the strangest phenomena in the universe. Imagine you have two particles that are entangled. You separate them by sending one to the other side of the galaxy. Now, if you measure one particle, the other particle instantly reacts, no matter how far apart they are. It's like they're connected by some invisible cosmic thread that transcends space and time. This isn't just some weird theory. Scientists have actually observed this happening in experiments. Now, you might be wondering, okay, this is all very strange, but does it actually matter in the real world? Well, it turns out that quantum mechanics isn't just about mind-bending theories. Scientists are now using these weird quantum properties to create some seriously cool technology. For example, they're working on super secure communication systems that use quantum entanglement. These systems are so secure that any attempt to eavesdrop on the communication would disturb the entangled state, immediately alerting the parties involved. It's like having a secret code that changes the moment anyone tries to crack it. But here's the thing that really blows my mind. Even after more than a century of research, nobody really understands why quantum mechanics works the way it does. We can use the math to make incredibly accurate predictions, but when it comes to explaining the underlying reasons for these strange behaviors, like superposition and entanglement, we're still pretty much in the dark. It's like we've stumbled upon the user manual for the universe, but it's written in a language we can't fully comprehend. Just when you thought quantum mechanics couldn't get any weirder, it throws us another curveball. We're about to dive into a principle that doesn't just limit what we know, but what we can know. It's like the universe itself is playing a cosmic game of hide and seek, and we're always one step behind. Back in 1927, a physicist named Werner Heisenberg came up with this mind-bending idea called the uncertainty principle. Basically, he figured out that you can't know everything about a particle at the same time. It's not because our tools aren't good enough or we're not smart enough. No, it's actually a fundamental limit of the universe itself. How wild is that? Here's how it works. The more precisely you measure a particle's position, the less you can know about its momentum, and vice versa. It's like trying to pin down a hyperactive toddler. The harder you try to grab them, the less you know about where they're going to run next. But in this case, it's not the toddler's fault. It's just how the universe works at its tiniest scales. This uncertainty principle isn't just some abstract idea that physicists came up with to make our heads hurt. It actually has real-world effects. For example, it affects how atoms behave and how chemical reactions work. When atoms are getting all cozy and reacting with each other, the uncertainty principle is there, messing with the energy states of electrons and influencing how fast reactions happen and what pathways they take. But wait, it gets even weirder. This fuzziness at the quantum level leads to something called quantum tunneling. Imagine you're trying to roll a ball up a hill, but it doesn't quite have enough energy to make it to the top. In our everyday world, that ball's just going to roll back down. But in the quantum world, there's a chance, a small one, but still a chance, that the ball could just pop up on the other side of the hill. It's like it tunneled right through the hill itself. This quantum tunneling isn't just some cool party trick. It's actually super important for how our universe works. For example, it's essential for nuclear fusion in stars. Without quantum tunneling, hydrogen nuclei wouldn't be able to get close enough to fuse together and release energy. The repulsive forces between their positive charges would keep them apart. But thanks to tunneling, they can bypass this barrier and get the party started. We're even using quantum tunneling in some of our technology. There's this thing called a scanning tunneling microscope that lets us see individual atoms. It works by exploiting the tunneling of electrons. And if you've ever used flash memory, like in your phone or computer, you're benefiting from quantum tunneling too. The electrons in these devices tunnel through insulating layers to store information. Now, let's get a bit philosophical for a moment. The uncertainty principle raises some pretty big questions about determinism in the universe. If we can't know both the position and momentum of particles at the same time, how can we predict everything that's going to happen? It's like the universe is telling us, sorry folks, but you can't have all the information at once. Some scientists even think the uncertainty principle might explain why the universe exists at all instead of just being empty as space. It's like the fabric of reality itself is built on this inherent fuzziness. Maybe without this uncertainty, everything would just cancel out and we'd be left with nothing. The uncertainty principle shows us that there's a limit to what we can know about the universe. It's not just about our knowledge being limited, but about reality itself having these built-in restrictions. It's like we're trying to read a book, but some of the pages are always blurry. We can make out the general story, but we'll never be able to see every single detail at once. From blurry pages in the book of reality, we're about to zoom in even further. But instead of finding more uncertainty, we'll discover a hidden symphony. What if the fundamental building blocks of our universe weren't particles at all, but impossibly small vibrating strings? This is the mind-bending world of string theory, where reality gets even weirder than we thought possible. String theory is like the ultimate puzzle piece that physicists have been searching for. It's trying to solve one of the biggest problems in physics: how to combine Einstein's theory of relativity with quantum mechanics. These two theories work great on their own, but they don't play nice together when we try to describe the whole universe. That's where string theory comes in, offering a way to potentially unite these two pillars of modern physics. But here's where things get really wild. For string theory to work, we need a universe with way more dimensions than we can see or even imagine. We're used to thinking about our world in 3 spatial dimensions plus time, but string theory says there could be as many as 10 or 11 dimensions. It's like our universe is just the surface of a much larger, higher dimensional reality that we can't perceive. Now, let's talk about what these strings actually are. In string theory, particles aren't really points like we usually think of them. Instead, they're tiny loops of energy vibrating in different ways. It's kind of like a cosmic guitar. Just like a guitar string can vibrate to make different notes, these cosmic strings vibrate to create different particles. Every particle we know about, electrons, quarks, photons, they're all just different vibrations of these fundamental strings. This idea is so complex that nobody has been able to fully work out the math, even after decades of work. It's like we've stumbled upon a beautiful symphony, but we can only hear a few notes at a time. We're still trying to piece together the full score. Some versions of string theory take things even further. They suggest there could be parallel universes, or that our universe is just a giant hologram. It's like we're living in a sci-fi movie, but it's actually serious science. These ideas come from something called M-theory, which combines different string theories into one big framework. M-theory proposes that strings can exist in higher dimensional spaces, and that our universe might be just one of many within a larger multiverse. There's also something called brain theory, which is another variant of string theory. It suggests that our universe could be a 3-dimensional brain embedded in a higher dimensional space. And get this, other dimensions could have completely different physical laws. It's like our universe is just one page in a cosmic book, with each page having its own unique set of rules. The problem is, we can't test any of this yet. The energies needed to observe these strings or extra dimensions are way beyond what our particle accelerators can do. It's like trying to see individual atoms with a magnifying glass. We just don't have the tools yet. This is why some critics argue that string theory, despite its mathematical beauty, lacks experimental evidence. So where does this leave us? String theory is either the ultimate theory of everything or a beautiful mathematical dead end, and we still don't know which. It's like Schrödinger's cat, but for the entire universe, both revolutionary and potentially meaningless at the same time. But even if string theory turns out to be wrong, it's already changed how we think about the universe. It's pushed us to consider new possibilities and ask questions we never thought to ask before. And some of the ideas from string theory are helping us understand other weird parts of the universe, like black holes. It's important to note that string theory isn't the only game in town when it comes to unifying physics. There are other approaches like loop quantum gravity that offer different perspectives on how to bring gravity and quantum mechanics together. These alternative theories propose that space-time itself might be quantized, made up of discrete loops rather than being smooth and continuous. From invisible strings to invisible monsters, our cosmic journey is about to take a dark turn. We're diving into the realm of black holes, where reality as we know it ceases to exist. These cosmic devourers aren't just sci-fi fantasies. They're real, and they're changing everything we thought we knew about the universe. Black holes are like cosmic monsters, gobbling up everything that comes too close. Even light itself can't escape their grasp. They form when massive stars collapse under their own gravity, creating a point of infinite density called a singularity. But here's where things get really weird. At the edge of a black hole, called the event horizon, time and space switch places. It's like the universe is playing a cosmic prank on us, flipping everything we thought we knew about reality on its head. If you were to fall into a black hole, which I don't recommend by the way, you'd see some pretty wild stuff. As you cross the event horizon, you'd witness the entire future of the universe flash before your eyes. It's like the ultimate binge watch, but with a lot more existential dread. And once you're inside the black hole, well, that's where things get even weirder. Our laws of physics break down completely, and we have no idea what happens at the singularity. It's like trying to divide by zero. It just doesn't compute. But scientists aren't giving up on understanding these cosmic mysteries. Some researchers think that information that falls into a black hole might be stored on its surface, like a cosmic hologram. This idea, called the holographic principle, has connections to string theory and might help us understand quantum gravity. It's like the universe is playing a game of 3D chess, and we're just starting to figure out the rules. In 2019, scientists actually took a picture of a black hole for the first time using a network of telescopes across the Earth. This groundbreaking image showed us a glowing ring of light encircling the shadow of an incredibly dense object in the galaxy M87. It's like we finally got a glimpse of the monster that's been hiding in the cosmic closet all this time. But black holes aren't just cosmic vacuum cleaners. They're windows into the deepest mysteries of space, time, and quantum mechanics. Take Hawking radiation, for example. This idea, proposed by the brilliant physicist Stephen Hawking in 1974, suggests that black holes aren't entirely black. They emit faint radiation due to quantum effects near the event horizon, causing them to lose mass and eventually evaporate. It's like the universe's way of saying, nothing lasts forever, not even black holes. This leads us to one of the biggest head-scratchers in physics, the black hole information paradox. It's all about what happens to the information contained within objects that fall into a black hole. If a black hole evaporates completely, does the information get lost forever? This would contradict the principle that information cannot be destroyed. It's like trying to solve a cosmic jigsaw puzzle where the pieces keep disappearing. Gerard 't Hooft, another brilliant mind in the world of physics, proposed a solution. He suggested that the information entering a black hole might not be lost, but instead stored on the event horizon. It's as if the three-dimensional information is encoded on the two-dimensional surface of the black hole. This idea ties back to the holographic principle we mentioned earlier, showing how different concepts in physics are all interconnected. At the heart of every black hole lies a singularity, a point of infinite density where the known laws of physics break down. It's like the ultimate "here be dragons" on the map of the universe. This singularity raises profound questions about the nature of reality and the limits of our understanding. We're like explorers standing at the edge of a cosmic abyss, peering into the unknown. But wait, it gets even weirder. Roger Penrose, a physicist with some seriously out there ideas, proposed the concept of a naked singularity. This is a singularity that could exist without an event horizon, exposing its chaotic nature to the universe. It's like a black hole without its cosmic cloak, potentially violating the cosmic censorship hypothesis. The idea of naked singularities is so wild that most physicists think they can't exist in nature. But the fact that we're even considering them shows how black holes push the boundaries of our understanding. Just when you thought the universe couldn't get any weirder, we're about to dive into a mystery that makes black holes look simple. Imagine a universe where most of the stuff in it is completely invisible. Well, you don't have to imagine. That's the reality we're living in. We're talking about dark matter, and it's like a giant invisible web stretching across the entire universe, holding galaxies in place. This cosmic mystery started back in the 1930s when astronomers noticed something really strange. Galaxies were spinning way too fast. According to the laws of physics we knew at the time, these galaxies should have been flying apart. But they weren't. It was like there was some invisible force holding them together. This was the first clue that led scientists to propose the existence of dark matter. Now, here's where things get really wild. Dark matter makes up about 85% of all the matter in the universe. That's right, most of the stuff out there isn't stars or planets or anything we can see. It's this invisible substance that we can't directly observe. And the craziest part? We have no idea what it's actually made of. Scientists have been trying to figure this out for decades. They've built these huge detectors deep underground to try and catch dark matter particles. These detectors are like cosmic fishing nets, waiting to snag a dark matter particle as it passes through. But so far, they haven't caught anything. It's like trying to catch a ghost with a butterfly net. Some scientists think dark matter might be made of tiny particles called WIMPs. That stands for weakly interacting massive particles. They're hypothetical particles that would interact through gravity and the weak nuclear force. Others think it could be made of strange particles called axions. These theoretical particles could help solve some problems in quantum physics and might also play a role in dark matter. There are even some wild theories that dark matter could be made up of tiny primordial black holes. These would be black holes that formed right after the Big Bang, way smaller than the ones we usually think about. It's like the universe is playing a cosmic game of hide and seek, and we're still trying to figure out where all the matter is hiding. But here's where it gets really interesting. Dark matter isn't just floating around randomly. It forms this incredible structure called the cosmic web. Imagine a giant 3D spider web stretching across the entire universe. The threads of this web are made of dark matter, and galaxies are clustered along these threads. In between the threads are these huge empty voids. It's like the universe has this invisible skeleton that everything else is built around. This cosmic web is crucial to understanding how the universe is structured. It's like dark matter is the architect of the cosmos, designing where galaxies and galaxy clusters form. When we look at maps of the universe, we can see these filaments and voids, even though we can't directly see the dark matter itself. It's like looking at the wake of a boat in water. We can't see the boat, but we can see how it affects its surroundings. Scientists are using all kinds of creative methods to try and detect dark matter. Some are looking for subtle gravitational effects. Others are trying to create dark matter particles in particle accelerators. There are even experiments looking for dark matter in old rocks from deep underground. It's like a cosmic treasure hunt, and every scientist is using a different map. Understanding dark matter isn't just about solving a cosmic mystery. It's about understanding the basic structure of the universe itself. It's like we've been living in a house our whole lives, and suddenly we realize that most of the house is invisible. Figuring out what dark matter is could completely change our understanding of physics, the universe, and our place in it. Just when we thought we had a handle on the universe's invisible architecture, another cosmic enigma emerges from the shadows. What if there's a force so powerful it's literally tearing space apart at the seams? Welcome to the mind-bending world of dark energy, where the universe's expansion isn't just continuing, it's accelerating. In the late 1990s, astronomers made a shocking discovery that turned our understanding of the cosmos upside down. They found out that the expansion of the universe is speeding up. This was completely unexpected and went against everything we thought we knew about gravity. According to our previous understanding, gravity should have been slowing down the expansion of the universe over time. But instead, something was pushing everything apart faster and faster. This mysterious force was given the name dark energy, and it's one of the biggest puzzles in modern physics. What's even more mind-blowing is that dark energy makes up about 68% of the universe's energy and matter. That's right. More than 2/3 of the universe is composed of something we can't see, touch, or even begin to explain. It's like discovering that most of your house is made of an invisible substance you never knew existed. Scientists have been scratching their heads trying to figure out what dark energy actually is. One leading theory suggests that it could be a property of empty space itself. This idea, called vacuum energy, implies that even a perfect vacuum isn't truly empty. Instead, it's filled with fluctuating virtual particles that pop in and out of existence. These quantum fluctuations could create a kind of negative pressure that pushes space apart. Another hypothesis proposes that dark energy might be a dynamic field known as quintessence. This field could change over time and influence the universe's expansion in a more complex way than a simple constant force. The idea of quintessence is exciting because it opens up the possibility that the effects of dark energy could vary across different regions of space or different periods in the universe's history. The concept of a cosmological constant, originally introduced by Einstein and later abandoned, has made a surprising comeback in light of dark energy. It's now seen as a crucial component in explaining the accelerated expansion of the universe. However, there's a huge problem when scientists try to calculate its value using quantum theory. The results are off by a staggering 120 orders of magnitude compared to what we observe. This mind-boggling discrepancy is known as the vacuum catastrophe, and it's one of the most perplexing issues in theoretical physics. What's really wild about dark energy is that its effects are so dramatic despite its incredibly small density. If you could somehow collect all the dark energy in a volume the size of the Earth, it would have about the same mass as a small grain of sand. But when you spread that tiny amount across the vast expanses of the cosmos, it becomes powerful enough to overcome the gravitational pull of all the visible matter in the universe. The implications of dark energy for the future of the universe are pretty intense. If it continues to increase in strength, it could lead to a scenario known as the Big Rip. In this apocalyptic vision of the future, the expansion of the universe would accelerate to the point where even atoms are torn apart. Everything from galaxies to planets to the very fabric of matter itself would be shredded by the overwhelming force of dark energy. Scientists aren't just sitting around theorizing about dark energy. They're actively trying to measure its effects. Current and planned experiments are studying distant supernovae and the cosmic microwave background to get insights into the universe's expansion history. These observations act like cosmic milestones, allowing us to track how the rate of expansion has changed over billions of years. It's worth noting that not everyone is convinced that dark energy is the answer to our cosmic acceleration problem. Some theories propose alternative explanations that don't rely on this mysterious force. These ideas suggest modifications to our understanding of gravity or the existence of additional dimensions that could account for the observed phenomena. While these alternative theories are intriguing, they're still very much in the minority compared to the dark energy hypothesis. Just when we thought we had a handle on the universe's invisible architecture, another cosmic enigma emerges from the shadows. But this time, we're not looking at the future of the universe or its mysterious dark components. Instead, we're peering back in time to the very beginning of everything. Imagine if you could tune your old TV to pick up a signal from the beginning of time. That's not too far off from what actually happened in 1964, when two astronomers stumbled upon a discovery that would revolutionize our understanding of the cosmos. It all started with a faint radio hum that seemed to come from every direction in the sky. At first, Arno Penzias and Robert Wilson thought they had a problem with their equipment. They even cleaned out pigeon droppings from their antenna, thinking that might be the cause of the strange signal. But no matter what they did, the hum persisted. Little did they know, they had just discovered the cosmic microwave background radiation, the afterglow of the Big Bang itself. This cosmic microwave background, or CMB for short, is like a baby picture of our universe. It's the oldest light we can see, dating back to when the universe was just 380,000 years old. Now, that might sound pretty old, but in cosmic terms, it's practically infancy. To put it in perspective, if the entire history of the universe was compressed into a single year, this light would have been emitted on January 1st, just after midnight. What's really mind-blowing about the CMB is how uniform it is. We're talking about a temperature difference of only about 1 part in 100,000 across the entire sky. That's like having a perfectly smooth beach with only a few grains of sand, slightly out of place. But those tiny imperfections are actually incredibly important. They're like cosmic seeds that eventually grew into all the galaxies, stars, and planets we see today. Scientists have been mapping this cosmic background radiation in incredible detail using specially designed satellites. The Wilkinson Microwave Anisotropy Probe, WMAP, and later the Planck satellite have given us the most precise measurements of the age, composition, and shape of the universe we've ever had. It's like we've been able to take the universe's fingerprints and run them through the cosmic equivalent of CSI. These maps have revealed some pretty wild things about our universe. For one, they've shown us that the universe is flat. Not flat like a pancake, but flat in the sense that parallel lines will always stay parallel, even over vast cosmic distances. This might not sound too exciting, but it has huge implications for the fate of the universe and how it all began. Speaking of beginnings, the CMB has also given us evidence for something called cosmic inflation. This is the idea that in the tiniest fraction of a second after the Big Bang, the universe expanded faster than the speed of light. It's like the cosmos hit the turbo button and went from subatomic to vast in the blink of an eye. This rapid expansion helps explain why the CMB is so uniform across such vast distances. By studying this ancient light, scientists can test their theories about how the universe began and evolved. It's like having a time machine that lets us peek back to the earliest moments of cosmic history. We can see how the first structures formed, how matter and energy were distributed, and even get clues about the nature of dark matter and dark energy. The cosmic microwave background is also helping us understand the balance of different types of matter and energy in the universe. It's like we've been able to weigh the cosmos and figure out what it's made of. And the results are pretty surprising. Normal matter, the stuff we can see and touch, only makes up a tiny fraction of the universe. The rest is that mysterious dark matter and dark energy we've talked about before. From the vast cosmic scales we've been exploring, we're about to zoom into the tiniest building blocks of reality. What if I told you there's a particle so fundamental, yet so elusive, that it took nearly 5 decades and the largest machine ever built by humans to find it? The hunt for the Higgs boson reads like a scientific detective story, with plot twists that would make even the most imaginative sci-fi writers envious. For decades, physicists had a big problem in their theories. They couldn't figure out why some particles have mass while others don't. It's like trying to understand why some people sink in a pool while others float, but on a cosmic scale. This wasn't just a minor detail they could ignore, it was a fundamental question that threatened to unravel our entire understanding of the universe. In 1964, a group of physicists, including Peter Higgs, came up with a wild idea. They proposed that there's this invisible field that permeates all of space, kind of like a cosmic molasses that other particles stick to. This field, which we now call the Higgs field, is what gives particles their mass. The more a particle interacts with this field, the more mass it has. Think of it like this: the Higgs field is like a cosmic swimming pool. Some particles are like Olympic swimmers, cutting through the water with barely any resistance. These particles, like photons, have very little mass. Other particles are like me trying to swim. They interact a lot with the water and move much more slowly. These particles have more mass. Of course, proposing a field is one thing, but proving it exists is another. Scientists realized that if this field existed, there should be a particle associated with it, the Higgs boson. Finding this particle became one of the biggest quests in physics. It was like searching for a cosmic needle in a universal haystack. To find this particle, scientists had to build the largest and most complex machine ever created, the Large Hadron Collider. This massive particle accelerator, buried deep underground near Geneva, Switzerland, is a 27-kilometer ring where protons are smashed together at nearly the speed of light. The hope was that these high-energy collisions would create Higgs bosons that could be detected. After decades of searching and billions of dollars spent, scientists finally struck gold in 2012. They announced the discovery of a particle that matched the predictions for the Higgs boson. It was a moment of triumph for physics, confirming decades of theoretical work and completing the standard model of particle physics. But the Higgs boson isn't an easy particle to study. It's incredibly unstable, existing for only a tiny fraction of a second before decaying into other particles. Imagine trying to photograph a soap bubble that pops almost as soon as it forms. That's the challenge scientists face when studying the Higgs boson. The discovery of the Higgs boson was a massive achievement, but like all great scientific discoveries, it opened up even more questions. Some scientists think there might be multiple types of Higgs bosons, each with different properties. Others speculate that the Higgs field might be connected to cosmic inflation, the rapid expansion of the universe in its earliest moments. As we loop back to quantum mechanics, we'll see how the Higgs connects to some of the deepest mysteries in physics. It's not just about understanding mass anymore, it's about understanding the fundamental nature of reality itself. The Higgs boson might hold clues to the nature of dark matter, or help us understand what happened in the first moments after the Big Bang. Now, just when you thought physics couldn't get any weirder, we're about to dive into a phenomenon that even Einstein found too bizarre to believe. It's a quantum connection so powerful, it seems to ignore the very fabric of space-time. Welcome to the mind-bending world of quantum entanglement, where reality gets seriously twisted. Imagine two particles that are forever linked, no matter how far apart they are. This isn't science fiction, it's the reality of quantum entanglement, and it's about to get even stranger. Einstein famously called this phenomenon spooky action at a distance, and thought it showed that quantum mechanics was incomplete. But as it turns out, entanglement is not only real, it's one of the most important and mind-boggling aspects of quantum physics. When particles are entangled, measuring one instantly affects the other, even if they're on opposite sides of the universe. This seems to violate Einstein's special relativity, which says nothing can travel faster than light. But here's the catch. It doesn't actually send information. It's more like the particles are somehow connected outside of space and time itself. Scientists have created entangled particles separated by hundreds of miles and even sent them to space, proving that this weird quantum link really does exist. Now, you might be thinking, okay, that's cool, but what's the point? Well, it turns out that quantum entanglement isn't just a quirky party trick for physicists. It's actually the key to some of the most exciting developments in technology and our understanding of the universe. Let's talk about quantum computing for a second. This is where entanglement really shines. Quantum computers use entangled particles to perform calculations that would take classical computers billions of years to solve. It's like having a supercomputer on steroids, able to crunch through impossibly complex problems in a fraction of the time. This could revolutionize fields like drug discovery, weather prediction, and even break encryption systems that we currently rely on for secure communication. Speaking of communication, quantum entanglement is also being used to create super secure communication systems. These systems use the principles of entanglement to ensure that any attempt to eavesdrop on the communication would be detectable. It's like having a secret code that's impossible to crack, because the very act of trying to crack it gives you away. This level of security is so high that it's unattainable by any classical methods we currently have. But the implications of quantum entanglement go way beyond just practical applications. Some physicists are starting to think that entanglement might be connected to the very nature of space-time itself. This idea raises some mind-bending questions about the underlying structure of reality. Are the particles we observe just the surface-level manifestations of a deeper, more interconnected reality? Could entanglement be the key to understanding gravity, or the fabric of the universe? The phenomenon of quantum entanglement challenges our classical intuitions about locality and separability. It suggests that particles can be interconnected in ways that defy traditional notions of space and time. This has profound implications for our understanding of the universe and the interconnectedness of all things. It's like the universe is playing a cosmic game of connect the dots, but all the dots are connected to each other at the same time. Some researchers have even suggested that quantum entanglement might play a role in consciousness. While this idea is still highly speculative, it's fascinating to consider how the quantum world might influence our own thoughts and experiences. Could our brains be using quantum processes to create consciousness? It's a wild idea, but in the world of quantum mechanics, sometimes the wildest ideas turn out to be true. As we continue our journey through the quantum realm, we're going to see how these strange quantum connections might even lead to new ways of thinking about reality itself. The deeper we go into the quantum world, the more we realize that our everyday understanding of the universe is just the tip of the iceberg. There's a whole world of weird and wonderful phenomena happening at the quantum level, and entanglement is just the beginning. If you thought quantum entanglement was mind-bending, prepare yourself for a theory that takes quantum strangeness to a whole new level. We're about to explore an idea that makes entanglement look downright normal. What if, instead of particles collapsing into a single state when measured, the universe itself splits into multiple realities? This isn't just wild speculation, it's a compelling interpretation of quantum mechanics that's captivated physicists for decades. Welcome to the mind-blowing world of the many worlds interpretation. The many worlds interpretation, or MWI for short, was first proposed by Hugh Everett III back in 1957. Everett was trying to solve a big problem in quantum mechanics, the quantum measurement problem. You see, in quantum mechanics, particles exist in a state of superposition, meaning they can be in multiple states at once until we measure them. But what happens when we make that measurement? The traditional view says the particle collapses into a single definite state. But Everett had a different idea. What if there's no collapse at all? What if all the possibilities actually happen just in different universes? This is where things get really wild. According to the many worlds interpretation, every time a quantum event occurs, the universe branches into multiple parallel realities. Each of these branches represents a different outcome of that quantum event. So in one universe, you might measure an electron spinning one way, and in another universe, you measure it spinning the other way. Both outcomes are equally real. They just exist in separate, non-communicating branches of the universe. Now you might be thinking, okay, that's pretty weird, but what does it mean for me? Well, hold on to your hat because it gets even crazier. If the many worlds interpretation is correct, it means there could be infinite versions of you living out every possible life in parallel universes. In one universe, you decided to keep reading this video. In another, you fell asleep 5 minutes ago. There's a universe where you became an astronaut and another where you're a world-famous rock star. Every decision you've ever made, every coin flip, every random quantum event has created new branches of reality. This idea might sound like something out of a sci-fi novel, but it's a serious scientific theory with some interesting implications. For one thing, it could potentially explain quantum phenomena without needing a mysterious collapse of the wave function. In the many worlds view, there's no need for collapse because all possibilities are realized just in different universes. The many worlds interpretation also has some intriguing connections to the field of quantum computing. In a quantum computer, calculations happen in a state of superposition with multiple possibilities being explored simultaneously. Some scientists have suggested that this could be explained by the computations literally happening in parallel universes. It's a mind-bending idea that pushes the boundaries of what we consider possible in computation. But of course, there's a big problem with the many worlds interpretation. How do you test an idea about parallel universes that we can never see or interact with? This is one of the main criticisms of the theory. It leads to what some scientists call an extravagant proliferation of universes, raising questions about whether these unobservable branches can be considered physically real. There are also alternative interpretations of quantum mechanics that offer different explanations. The Copenhagen interpretation, for example, suggests that the act of measurement causes the wave function to collapse into a single outcome. This contrasts sharply with the many worlds view that all outcomes occur. Despite these challenges, the many worlds interpretation remains a fascinating and influential idea in physics. It challenges our conventional understanding of reality and raises deep philosophical questions about the nature of existence and observation. Are we really living in just one of an infinite number of parallel universes? Is every possibility played out somewhere in the multiverse? As we loop back to our discussion of relativity, we can see how these quantum ideas connect to our understanding of time and causality. The many worlds. Interpretation suggests a view of reality that's far stranger and more complex than our everyday experience would suggest. It's a reminder of how weird and wonderful the universe can be at its most fundamental level. Just when you thought quantum mechanics couldn't get any weirder, we're about to explore a mystery that's been puzzling physicists for centuries. Why does time only flow in one direction? It's a question that seems simple on the surface, but as we'll see, it leads us down a rabbit hole of entropy, causality, and the very nature of reality itself. We can remember the past, but we can't remember the future. Hot coffee cools down, but cold coffee doesn't spontaneously heat up. These everyday experiences all point to a fundamental property of our universe. Time has a direction. But here's the thing. The laws of physics don't actually care which way time flows. If you were to watch a video of particles interacting and then play it in reverse, both versions would be equally valid according to the laws of physics. So why do we experience time as moving forward? The answer lies in a concept called entropy, which is essentially a measure of disorder in a system. In the 19th century, a physicist named Rudolf Clausius introduced the concept of entropy and realized that in any isolated system, entropy always increases. This led to the formulation of the second law of thermodynamics, which explains why your coffee gets cold but never spontaneously heats up. As time passes, things tend to become more disordered and spread out. This increase in entropy is what gives time its arrow, pointing from the past to the future. But this raises another question. If entropy always increases, why did the universe start in such a low entropy state? The moments following the Big Bang were incredibly ordered, which is kind of weird when you think about it. Some physicists have proposed that the universe itself acts as an entropy-generating machine. As it expands, new space forms, creating more opportunities for entropy to increase. It's like the universe is constantly making more room for things to get messy. Now, if we zoom in to the level of individual particles, things get even stranger. At this tiny scale, there's no arrow of time. Particles can move forwards or backwards without breaking any physical laws. This disconnect between the microscopic and macroscopic worlds is one of the biggest puzzles in physics. How do we get from time-symmetric particles to our time-asymmetric experience of reality? Some physicists think the arrow of time might be connected to other big cosmic phenomena. Maybe it's linked to the expansion of the universe, or even to quantum entanglement. Others have even more radical ideas. Julian Barber, for example, suggests that time might not exist at all. He envisions the universe as a timeless landscape where all moments exist simultaneously. In this view, our perception of time as a linear progression is just an illusion. The concept of entropy doesn't just explain why your ice cream melts. It also has profound implications for the fate of the universe. As entropy increases, the universe moves towards a state of maximum disorder. This end state is sometimes called the heat death of the universe, where everything reaches the same temperature and no energy gradients exist. It's a cold, dark, static cosmos where nothing really happens anymore. Kind of a bummer, right? But don't worry too much about the heat death just yet. Some physicists have proposed ways the universe might avoid this fate. The multiverse hypothesis, for instance, suggests that our universe is just one bubble in an infinite cosmic foam. Most of these bubble universes might have started with high entropy, making our low-entropy universe a rare statistical fluke. This could explain why our universe seems so finely tuned for life. We just happen to be in one of the rare bubbles where things worked out. The arrow of time is deeply connected to our understanding of causality, the idea that effects always follow causes. This seems obvious in our everyday lives, but when you start thinking about time travel or quantum mechanics, things get complicated. If time isn't fundamental, how do we explain the apparent cause and effect relationships we see all around us? Understanding the arrow of time isn't just about solving an abstract physics problem. It's about understanding why we experience reality the way we do. Why do we remember the past but not the future? Why do we feel like we're moving through time? These questions touch on deep philosophical issues about the nature of consciousness and free will. Just when you thought the universe couldn't get any weirder, we're about to explore a theory that suggests our entire cosmos inflated from a pinpoint to cosmic proportions faster than you can blink. This wild idea of cosmic inflation isn't just mind-bending. It might explain why our universe looks the way it does, and it could even mean we're just one bubble in an infinite ocean of realities. So let's rewind to the early 1980s when physicists were scratching their heads over some big problems with the Big Bang theory. Don't get me wrong, the Big Bang explains a lot, but it couldn't quite account for why the universe is so incredibly flat and uniform. I mean, if you look out into space in any direction, it pretty much looks the same, which is kind of weird when you think about it. Enter cosmic inflation, a theory proposed to address these head-scratchers. The idea is that right after the Big Bang, the universe underwent this crazy rapid expansion, doubling in size over and over again in tiny fractions of a second. We're talking about an expansion that happened faster than the speed of light, which sounds impossible, but it's actually allowed by the laws of physics because it's space itself that's expanding, not stuff moving through space. This rapid expansion helps to explain why the universe appears so uniform and isotropic on large scales. It's like if you had a tiny wrinkled balloon and then suddenly blew it up to the size of the Earth. Those wrinkles would be stretched out so much you'd hardly notice them. In the same way, any irregularities from the initial conditions of the Big Bang would have been smoothed out by this rapid expansion. But here's where things get really wild. Inflation theory doesn't just solve these problems, it opens up a whole new can of worms. See, some versions of the theory suggest that inflation is a perpetual process creating new universes continuously as space expands. This leads to the mind-bending concept of a multiverse, where our universe is just one bubble in an infinite sea of universes. Now you might be thinking, okay, but how could we ever know if other universes exist? And that's a great question. The thing is, each of these bubble universes could have different physical laws and constants. In some universes, the force of gravity might be stronger or weaker. In others, the speed of light could be different. This idea actually provides a potential explanation for something called the fine-tuning problem in cosmology. The fine-tuning problem is basically asking why the fundamental constants of our universe are so perfectly set to allow for the existence of life. It's like someone fine-tuned the universe just for us. But in a multiverse scenario, it's not so surprising that we find ourselves in a universe with the right conditions, because there could be countless other universes with different constants where life as we know it could never arise. Of course, all of this is still theoretical. Scientists have been looking for evidence to support cosmic inflation, and they've found some promising signs. Measurements of the cosmic microwave background radiation, which is like the afterglow of the Big Bang, show patterns that are consistent with what inflationary models predict. Experiments like the Planck satellite have provided really detailed maps of this cosmic microwave background, supporting the idea of a rapid expansion in the early universe. But here's the thing, direct evidence of inflation is still pretty elusive. And when it comes to the multiverse, well, that's even trickier. Some scientists argue that because other universes are inherently unobservable, the multiverse hypothesis might not be scientifically testable. This raises some big questions about what we consider a legitimate scientific theory. As we loop back to quantum mechanics, we'll see how these cosmic ideas actually connect to some of the strangest phenomena in the subatomic world. The concept of parallel realities in the multiverse isn't too far off from the idea of superposition in quantum mechanics, where particles can exist in multiple states at once until they're observed. Just when you thought quantum mechanics couldn't get any weirder, we're about to explore a theory that suggests the very fabric of space-time might be more like a frothy sea of bubbles than the smooth continuum we perceive. This mind-bending concept, known as quantum foam, challenges everything we think we know about the nature of reality at its tiniest scales. Quantum foam is the idea that, at the smallest possible scale, space-time isn't smooth at all. Instead, it's made up of tiny, fluctuating bits that are constantly popping in and out of existence. This isn't just empty speculation, it's a natural consequence of applying quantum mechanics to the structure of space and time itself. To understand quantum foam, we need to zoom in to an incredibly tiny scale called the Planck scale. This is about 10⁻⁵ meters, which is way smaller than even the tiniest subatomic particles we can observe. At this scale, quantum mechanics predicts that the energy of empty space isn't actually zero. Instead, it's filled with virtual particles that appear and disappear in the blink of an eye. These quantum fluctuations lead to the idea that space-time itself might be granular, or foamy, at the Planck scale. Imagine looking at a calm lake from a distance. It appears smooth and flat. But if you could zoom in to the molecular level, you'd see water molecules constantly moving and interacting. Quantum foam suggests that space-time works in a similar way, with tiny fluctuations creating a kind of fizziness at the smallest scales. This concept of quantum foam might explain some of the weird limitations we encounter in quantum mechanics. For example, the uncertainty principle tells us that we can't measure a particle's position and momentum perfectly at the same time. If space-time itself is fuzzy and fluctuating at the tiniest scales, it makes sense that there would be limits to how precisely we can measure things. But the implications of quantum foam go even further. Some theories propose that these quantum fluctuations could lead to the creation of tiny wormholes or even microscopic black holes. These would be incredibly short-lived, popping in and out of existence faster than we could possibly observe them. But their very possibility hints at a deeper connection between quantum mechanics and gravity, two areas of physics that have been notoriously difficult to reconcile. In fact, quantum foam is closely linked to attempts to unify quantum mechanics and gravity into a single theory. One approach called loop quantum gravity proposes that space-time itself is made up of discrete units, like a network of tiny loops. This is a radically different way of thinking about the structure of the universe, but it's one that naturally arises from the idea of quantum foam. Quantum foam might also provide insights into one of the biggest mysteries in cosmology, the cosmological constant problem. This is the huge discrepancy between the amount of energy we observe in empty space and what quantum mechanics predicts. The idea of quantum foam suggests that the vacuum of space isn't really empty at all, but filled with energy from these constant quantum fluctuations. This could potentially explain why space seems to have energy, even when it looks empty to us. Of course, actually observing quantum foam is an enormous challenge. We're talking about effects that happen at scales much smaller than an atom. Current technology is nowhere near sensitive enough to directly measure these fluctuations. It's like trying to see individual grains of sand from an airplane. We just don't have instruments precise enough to detect such tiny details. Despite these challenges, the concept of quantum foam opens up fascinating discussions about the hidden structure and energy of empty space. It suggests that even what we perceive as nothing is actually rich with potential, constantly bubbling with activity, at scales too small for us to see. From the bubbling quantum foam of space-time, we zoom out to consider a theory that's equally bizarre but on a cosmic scale. Imagine our entire universe as a hologram, not in the sci-fi sense, but as a mathematical principle that could solve some of the biggest puzzles in physics. The holographic principle suggests that reality might be far stranger than we ever imagined. This mind-bending idea emerged from the study of black holes, particularly the notion that the information about matter falling into a black hole is not lost, but rather encoded on its event horizon. Gerard 't Hooft proposed that the information falling into a black hole might be stored on its event horizon, suggesting that the three-dimensional phenomena inside the black hole could be described by data imprinted on its two-dimensional surface. This concept laid the groundwork for the holographic principle. Leonard Susskind took this idea and ran with it, proposing that the entire universe might operate under a similar principle. He suggested that our three-dimensional reality could be encoded on a distant two-dimensional boundary. This isn't saying we're living in some kind of computer simulation or that our world isn't real. It's more like saying that the 3D space we experience is an emergent property of a more fundamental 2D reality. Now, you might be wondering how we could possibly test something like this. After all, we're talking about the fundamental nature of reality itself. Well, scientists are actively working on it. They're looking for tiny fluctuations in space-time that could indicate the underlying structure of the universe as proposed by the holographic principle. It's like trying to see the pixels on a TV screen by looking really closely. The holographic principle has some interesting connections to other areas of physics we've talked about. It's closely tied to string theory and attempts to unify quantum mechanics with gravity. Some versions of this idea even suggest that the 2D surface might be at the edge of the observable universe, or even at the beginning of time. It's wild to think about, right? One of the most exciting aspects of the holographic principle is that it might help explain how gravity emerges from quantum mechanics. This has been a huge puzzle in physics for a long time. It could also shed light on why the universe appears to have 3 spatial dimensions. These are fundamental questions that have plagued physicists for decades, and the holographic principle offers a new way of approaching them. In 1997, Juan Maldacena came up with a theory known as the AD-CFT correspondence. This provided a concrete example of the holographic principle in action. Maldacena showed that a universe described by gravitational forces in 3 dimensions could be mathematically equivalent to a universe described by quantum mechanics in 2 dimensions. This was a huge breakthrough that gave physicists a way to actually work with these ideas. The holographic principle challenges our understanding of reality in a profound way. It suggests that the universe may not be as solid as we perceive it. If true, it implies that the fundamental description of reality might be simpler than it appears, with our experiences of depth and motion being emergent from a more fundamental 2-dimensional reality. It's like we're watching a 3D movie, but all the information is actually contained in the 2D film strip. This idea has some pretty mind-bending implications. It means that everything we experience, the chair you're sitting on, the air you're breathing, even your own body, might be projections from a 2D surface. It's important to note that this doesn't mean these things aren't real. They're still very much real and tangible. It's just that the fundamental nature of reality might be very different from what we perceive. The holographic principle also has implications for how we think about information in the universe. If all the information about our 3D world can be encoded on a 2D surface, it suggests there might be limits to how much information can be contained in any given region of space. This could have profound implications for our understanding of black holes, quantum mechanics, and the nature of information itself. We've explored some mind-bending ideas about the nature of reality, but now we're about to dive into what many consider the holy grail of physics. Imagine a theory so powerful, it could explain everything from the heart of a black hole to the birth of the universe itself. That's the promise of quantum gravity, a theory that aims to unite Einstein's theory of general relativity with the strange world of quantum mechanics. The quest for quantum gravity is like trying to solve the ultimate cosmic puzzle. We have these 2 incredible theories that work amazingly well in their own domains. General relativity gives us a beautiful picture of gravity as the curvature of space-time, explaining everything from the orbits of planets to the behavior of black holes. On the other hand, quantum mechanics reveals the bizarre nature of reality at the smallest scales, where particles can exist in multiple places at once and seem to communicate instantly across vast distances. But here's the problem. These theories don't play nice together. When we try to apply quantum mechanics to gravity or general relativity to the quantum world, things start to fall apart. It's like we're missing a crucial piece of the puzzle that would make everything fit together perfectly. This is where quantum gravity comes in, attempting to bridge the gap between these 2 fundamental pillars of physics. One of the biggest challenges in this quest is the sheer difference in strength between gravity and the other fundamental forces. Gravity is incredibly weak compared to the electromagnetic force or the strong nuclear force that holds atoms together. This huge disparity makes it incredibly difficult to reconcile gravity with the quantum world. It's like trying to hear a whisper in a room full of screaming people. The signal gets lost in the noise. Over the years, physicists have come up with some pretty wild ideas to tackle this problem. One of the most famous is string theory, which proposes that all particles are actually tiny vibrating strings in extra dimensions we can't see. It's a beautiful and elegant idea, but it's also incredibly complex and hard to test experimentally. Another approach called loop quantum gravity takes a different tack. Instead of adding extra dimensions, it suggests that space itself is made up of tiny loops or nodes at the quantum level. In this view, space-time isn't smooth and continuous, but more like a fabric woven from quantum threads. It's a fascinating idea that challenges our fundamental understanding of space and time. Some theories even propose that gravity might not be a fundamental force at all, but rather an emergent phenomenon arising from more basic quantum processes. This is a mind-bending concept that suggests the gravity we experience in our everyday lives might be a sort of illusion, emerging from deeper, more fundamental interactions at the quantum level. The potential implications of quantum gravity are staggering. If we could crack this code, we might finally understand what happens at the center of a black hole, where our current theories break down completely. We could potentially peer back to the very first moments of the Big Bang, unraveling the mysteries of how our universe came into existence. It could revolutionize our understanding of space, time, and the nature of reality itself. But here's the catch. Testing these theories is incredibly challenging. The energies required to observe the effects of quantum gravity are far beyond what our current particle accelerators can achieve. We're talking about energies that existed in the first fraction of a second after the Big Bang. It's like trying to recreate the conditions of the early universe in a laboratory, a task that's currently well beyond our technological capabilities. This is why quantum gravity remains one of the biggest unsolved problems in physics. It's a tantalizing mystery that has captivated the minds of some of the greatest scientists for decades. Solving it could completely rewrite our understanding of the universe, potentially unifying all of physics into a single, elegant theory. As we wrap up our journey through the strange world of theoretical physics, it's clear that the quest for quantum gravity ties together all the bizarre concepts we've explored. From the warping of space-time to the quantum foam of the vacuum, from the holographic principle to the possibility of parallel universes, all of these ideas are connected in the grand tapestry of quantum gravity. As we wrap up our journey through the strange world of theoretical physics, it's clear that we've only scratched the surface of the universe's deepest mysteries. But what if there was one equation that could explain everything in the universe? That's the dream of a theory of everything, and it's been the holy grail of physics for decades. Physicists have been searching for a unified theory that combines all forces and particles into one elegant framework, but creating such a theory is incredibly difficult. It needs to explain everything from the Big Bang to black holes to the behavior of subatomic particles, and that's no small task. String theory has been a leading candidate for a theory of everything for a while now. It proposes that the fundamental building blocks of the universe are not particles but tiny vibrating strings. This idea is pretty wild, and it requires some pretty mind-bending concepts like extra dimensions beyond the familiar 3 of space and 1 of time. The problem is, string theory is incredibly complex and really hard to test experimentally. We don't have particle accelerators powerful enough to see these tiny strings, so some scientists are starting to wonder if it's the right approach. There are other ideas out there too. Loop quantum gravity is another approach that tries to unify gravity with quantum mechanics. It suggests that space-time itself is made of discrete loops, kind of like a fabric woven from tiny threads. This is really different from how we usually think about space as smooth and continuous. Some physicists are even exploring completely new frameworks, maybe based on information theory or emergent phenomena. The idea is that maybe we need to rethink our whole approach to understanding the universe. A true theory of everything would have to explain some pretty big mysteries that are still stumping scientists today. It would need to tell us what dark matter is, which makes up about 85% of all the matter in the universe but we can't see or touch. It would also have to explain dark energy, which is causing the universe to expand faster and faster. And that's just the start. A complete theory might also need to address deep questions about the nature of time, consciousness, and why the universe exists at all. These are questions that blur the line between physics and philosophy. One of the biggest challenges in developing a theory of everything is explaining the fundamental constants of nature. These are numbers like the speed of light or the gravitational constant that seem to be perfectly tuned to allow for the existence of life. Even tiny changes to these constants could lead to a universe where stars couldn't form or atoms couldn't exist. This is called the fine-tuning problem, and it's a real head-scratcher. Some physicists think it might be explained by the idea of a multiverse, where there are many different universes with different physical laws and constants. We just happen to be in one that allows for our existence. The search for a theory of everything isn't just about scientific curiosity. It's also a deeply philosophical quest that challenges our understanding of reality. It raises questions about whether the universe needs to conform to human notions of simplicity and elegance. Maybe the universe is fundamentally messy and complicated, and our desire for a single, beautiful equation is just wishful thinking. On the other hand, the history of physics has shown that seemingly unrelated phenomena often turn out to have deep connections, so maybe a unified theory is out there waiting to be discovered. As we conclude our journey through theoretical physics, it's worth reflecting on what all these strange ideas mean for our place in the cosmos. The quest for a theory of everything shows us how far we've come in understanding the universe, but it also highlights how much we still have to learn. It's a reminder of the incredible complexity and beauty of the world around us, and the endless human drive to understand it all. Just when we thought we'd explored the deepest mysteries of the universe, we stumble upon the ultimate enigma: consciousness itself. What if the very essence of our awareness is intertwined with the fundamental laws of physics? This isn't just another scientific puzzle. It's a question that challenges the very foundation of how we perceive reality. For centuries, scientists have kept the mind and the physical world in separate boxes. But now, some bold thinkers are starting to question this divide, wondering if consciousness might be more than just a byproduct of our brains. Let's dive into one of the strangest ideas in modern science: the possibility that consciousness itself is connected to the fundamental laws of physics. It sounds like something out of a sci-fi novel, but some serious researchers are exploring this mind-bending concept. The question at the heart of this mystery is known as the hard problem of consciousness, a term coined by philosopher David Chalmers. It asks why physical processes in the brain produce subjective experiences. Why do we feel things? Why are we aware? These questions have stumped scientists and philosophers for ages, and despite all our advances in neuroscience, we're still scratching our heads. Some scientists are proposing wild ideas to tackle this problem. One of these is called integrated information theory. This theory suggests that consciousness pops up when information is meaningfully integrated in a complex system, like our brains. It's like saying consciousness emerges from the way our brains process and combine information. This idea is pretty out there, but it's got some serious scientists thinking. But wait, it gets even weirder. Some researchers are looking at the bizarre world of quantum mechanics for answers. They're proposing that quantum processes inside neurons might play a role in consciousness. It's like they're saying our minds are connected to that weird quantum realm where particles can be in two places at once and communicate instantly across vast distances. If this turns out to be true, it would mean our conscious experiences are linked to the most fundamental level of reality we know. And here's where it gets really wild. Some thinkers are proposing an idea called panpsychism. This suggests that consciousness might be a fundamental property of the universe, just like mass or charge. They're saying that every particle in existence might have a tiny sliver of awareness. It's like the entire universe is alive in some way. This idea intertwines consciousness with the very fabric of reality itself. It's a mind-blowing concept that challenges everything we think we know about the nature of existence. The relationship between consciousness and quantum mechanics raises some pretty deep questions about the nature of reality. Is consciousness an emergent property that just pops up when things get complex enough? Or is it something more fundamental, baked into the universe from the start? These questions are forcing us to rethink our understanding of what it means to be conscious and what reality actually is. One of the weirdest connections between consciousness and quantum mechanics is the measurement problem. This is the idea that the act of observing a quantum system causes it to collapse from a wave of probabilities into a single definite outcome. Some scientists wonder if consciousness itself might play a role in this collapse. It's like they're saying our minds might actually be influencing reality at the quantum level. This idea is super controversial, but it shows just how strange things get when we start thinking about consciousness and quantum mechanics together. There's also some speculation about quantum entanglement and consciousness. Entanglement is this weird quantum effect where particles remain mysteriously connected across vast distances. Some researchers think this might mirror the way different regions of the brain synchronize to produce unified experiences. It's like they're suggesting our conscious experiences might be held together by quantum connections. Of course, not everyone buys into these wild ideas. Many scientists argue that consciousness is just an emergent property of complex neural networks. They say we don't need quantum weirdness or universal consciousness to explain our experiences. But even these more down-to-earth explanations still struggle with the hard problem of consciousness. Why do we have subjective experiences at all? It's a question that continues to baffle even the smartest minds in science. As we wrap up our journey through theoretical physics, we're left with this ultimate mystery. How does a universe of mindless particles give rise to conscious experience? It's a question that challenges us to think about. The relationship between mind, matter, and the fundamental nature of reality. Are we just complex arrangements of atoms, or is there something more to our existence? The quest to understand consciousness is pushing the boundaries of science and philosophy, forcing us to confront some of the deepest questions about the nature of existence itself. As we venture into the future of physics, we're confronted with the exciting possibility that everything we've learned so far might just be scratching the surface. We've come a long way from Newton's apple falling from a tree to Einstein's mind-bending theories of relativity and the bizarre world of quantum mechanics. But there's still so much we don't understand about the universe. Dark matter and dark energy continue to elude us, and we're still grappling with fundamental questions about the nature of time and consciousness. The next big breakthroughs in physics might come from experiments that push the boundaries of our current technology. Larger particle accelerators could potentially reveal new particles or forces that we've never seen before. These discoveries could completely reshape our understanding of how the universe works at its most fundamental level. It's like we've been looking at the cosmos through a keyhole, and now we're about to open the door wide open. But it's not just about building bigger machines. Advanced quantum computers are in development, and they could be game changers for physics. These super powerful machines might be able to simulate complex quantum systems in ways that our current computers can't even begin to approach. This could help scientists understand all sorts of phenomena, from superconductivity to the conditions of the early universe. Imagine being able to recreate the first moments after the Big Bang in a computer simulation. That's the kind of power we're talking about. Our view of the universe is about to get a lot clearer, too. New telescopes are on the horizon that could give us an unprecedented look at the cosmic dawn, the time when the first stars and galaxies formed. This is like getting a glimpse of the universe's baby photos. We might finally be able to see how the cosmic structures we observe today first came into being. Some physicists are thinking even bigger. They're wondering if we might need a completely new framework for understanding reality. Our current models of physics have taken us far, but they still can't explain everything we observe. Some researchers are exploring ideas based on information theory or computational models. What if the universe is more like a giant computer than a collection of particles? It's a wild idea, but then again, so is the notion that time could slow down depending on how fast you're moving. And then there are the really out there ideas. Some scientists are seriously considering concepts that sound like they're straight out of science fiction. Additional dimensions beyond the three we can see and touch? Time travel? Communication with parallel universes? These might seem far-fetched, but remember that many of the ideas we now take for granted in physics once seemed just as crazy. The future of physics is full of possibilities, and it promises to reveal a universe even stranger and more wonderful than we can currently imagine. As we push the boundaries of what we know, we're likely to encounter phenomena that challenge our most basic assumptions about reality. It's an exciting time to be alive and curious about the cosmos. Did you know that the entire universe was once smaller than an atom? It's mind-boggling to think about, but this is where our cosmic story begins. We're going all the way back to the very beginning, to the moment of the Big Bang. This is the starting point of everything we know, the birth of time and space itself. But here's the thing. We don't actually know what caused the Big Bang. It's one of the biggest mysteries in science, and it's been puzzling researchers for decades. Scientists have come up with all sorts of theories to try and explain that first moment of creation, but none of them can fully account for what happened. Some think it might have been a quantum fluctuation in a pre-existing void. Basically, they're saying that there was nothing, and then a tiny random change at the quantum level caused everything to suddenly pop into existence. It's a wild idea, but it's one of the leading theories out there. Others have an even crazier idea. They propose that our universe is just one of many, constantly being born and dying. Imagine a cosmic bubble bath, with universes popping up and disappearing all the time. In this scenario, our universe is just one bubble in an infinite sea of possibilities. It's a concept that's hard to wrap your head around, but it's seriously being considered by some of the smartest people in physics. But the truth is, we're still in the dark about those first few fractions of a second. It's like trying to piece together a movie when all you have is the last frame. We can see the results of the Big Bang all around us, but we can't rewind the tape far enough to see how it all started. It's frustrating, but it's also exciting. It means there's still so much left to discover. What if the answer lies in a theory we haven't even thought of yet? Science is always evolving, and new ideas are constantly challenging what we think we know. Maybe the key to understanding the Big Bang is hiding in some obscure corner of physics, just waiting to be uncovered. It's a tantalizing thought, and it keeps researchers pushing forward, always looking for that next big breakthrough. Now, here's a mind-bending concept about the universe's origins that we've recently started to explore. The idea that our entire universe might be a hologram. I know, it sounds like something out of a sci-fi movie, but hear me out. This theory suggests that everything we see and experience in our 3D world is actually a projection of information stored on a 2D surface. It's like we're living inside a giant cosmic hologram. This holographic principle was first proposed by theoretical physicist Leonard Susskind in the 1990s. It's based on some pretty complex math and quantum mechanics, but the basic idea is that all the information about our universe could be encoded on a two-dimensional surface, kind of like how a computer stores information on a hard drive. And just like how a 2D image on a credit card can create the illusion of a 3D object, the information on this cosmic 2D surface could create the illusion of our 3D universe. It's a wild concept, but it actually helps solve some big problems in physics. For example, it could explain why black holes don't violate the laws of quantum mechanics, which has been a major headache for physicists for years. And some researchers think it might even help us understand the Big Bang itself. If our universe is a hologram, maybe the Big Bang was just the moment when this cosmic projection first started. As we zoom out from this cosmic birth, we find ourselves in a universe that's expanding faster than we can explain. This is another big mystery in modern cosmology. We've known for a while that the universe is getting bigger, but in the late 1990s, astronomers discovered something unexpected. The expansion is accelerating. It's like the universe is stepping on the gas pedal, and we don't know why. This acceleration doesn't make sense based on what we know about gravity. According to Einstein's theory of general relativity, the expansion of the universe should be slowing down over time as gravity pulls everything back together. But that's not what we're seeing. Instead, it's like there's some mysterious force pushing everything apart, and it's getting stronger over time. Scientists have given this force a name: dark energy. But dark, in this case, really means we have no idea what it is. It's estimated that dark energy makes up about 68% of the universe, which is pretty crazy when you think about it. The majority of our universe is made up of something we can't see, detect, or understand. From the mysteries of dark energy, we now zoom in on a cosmic dance that's been playing out for billions of years. It's the story of Earth's formation, and it's filled with more drama and near misses than you might expect. Imagine a cloud of gas and dust swirling in the vastness of space. This is where Earth's story begins, a process that took millions of years to unfold. We're watching the formation of our solar system, but Earth wasn't always the blue marble we know today. For billions of years, our planet was a hellscape of molten rock and toxic gases. The early Earth was shaped by a series of catastrophic impacts from asteroids and comets. These cosmic collisions played a crucial role in reshaping the planet's surface and atmosphere. It's like Earth was getting an extreme makeover, but instead of a team of designers, it had a bunch of space rocks doing the renovations. One of these impacts was particularly significant. Scientists believe it might have created our moon. This wasn't just a cool addition to our night sky, though. The formation of the moon actually changed Earth's orbit and rotation. It's like Earth suddenly got a new dance partner and had to learn some new moves. These changes had a big impact on the planet's climate and conditions for life. It took billions of years for Earth to cool down sufficiently to develop a stable atmosphere. This wasn't just a matter of turning down the thermostat. The timing of these geological and atmospheric changes was critical for life to eventually thrive. It's like Earth was slowly setting the stage for the greatest show in the universe, life itself. But here's where things get really interesting. Recent studies suggest that the conditions necessary for life weren't just a result of Earth's position in the solar system. It turns out that a series of cosmic coincidences played a big role too. One of these lucky breaks was the presence of a magnetic field that protects the planet from solar radiation. Without this invisible shield, life as we know it might never have developed. The formation of Earth and its subsequent evolution is a tale of perfect timing and cosmic coincidences. It's like the universe was playing a game of cosmic billiards, and all the balls just happened to fall into the right pockets to create our home planet. This highlights how Earth's development was intricately linked to its environment and the broader universe. But let's take a step back and think about what this means in the grand cosmic story. Earth's formation is just one chapter in the epic tale of the universe. It's a reminder that even in the vastness of space, small changes can have huge impacts. The same forces that shaped our planet are at work throughout the cosmos, creating and destroying worlds in an endless cycle. As we zoom out from Earth's formation, we find ourselves looking at the first humans to gaze up at the stars and wonder. These early stargazers didn't know about dark energy or the Big Bang. They couldn't have imagined the violent birth of our planet or the delicate balance of forces that made life possible. But they were the first to ask the big questions that would eventually lead to our current understanding of the universe. From those first curious humans gazing at the stars, we fast forward to a time when asking questions became an art form. Picture ancient Greece, where philosophers are about to stumble upon ideas so powerful they'll echo through the centuries. But here's the twist. Some of their wildest guesses about the universe were shockingly close to the mark. How did they do it? We're talking about a group of thinkers who didn't have fancy telescopes or particle accelerators. They were just regular people looking up at the night sky, trying to make sense of the world around them. But these ancient Greeks had something special. They relied on logic and observation to understand the cosmos. It's like they were playing a massive game of cosmic detective, using nothing but their minds and their eyes. Now, let's be real. They got a lot of things wrong, like really wrong. They thought the Earth was the center of the universe, which we now know is absolutely not true. But even with all their mistakes, these ancient philosophers were laying the groundwork for modern science. It's kind of wild to think about. These guys in togas were setting the stage for the mind-bending physics theories we have today. One of the coolest examples of this is Democritus. This dude came up with the idea of atoms way back in ancient times. He basically said that everything is made up of tiny, indivisible particles. Now, he didn't have a microscope or anything, he just used his brain to figure this out. And guess what? Modern atomic theory isn't that far off from what Democritus was talking about. It's like he had a crystal ball or something. But it wasn't just Democritus who was ahead of his time. We've got Aristotle, another big name in ancient Greek philosophy. This guy came up with the concept of causality, the idea that every effect has a cause. It sounds simple, but this idea is still super important in how we understand the universe today. Modern physics is all about figuring out cause and effect, so Aristotle's idea is still kicking around in science labs all over the world. Of course, not all of their ideas were winners. Take Ptolemy, for example. He was a big deal in ancient astronomy, but he got some things pretty wrong. He came up with this whole model of the universe where Earth was at the center, and everything else revolved around us. We know now that's not how it works at all, but Ptolemy's ideas were still important. Even though he was wrong, his work got people asking questions and trying to figure out how the universe really works. This is what's so cool about these ancient Greek philosophers. Even when they were wrong, they were pushing science forward. They were asking big questions about the nature of reality and existence, setting the stage for all the scientific exploration that came after them. It's like they were the first domino in a long line that leads right up to the physics we have today. Now, you might be wondering, if they got so much wrong, how can we say they were important for science? Well, it's all about the method. These ancient thinkers were emphasizing rational inquiry, the idea that we can use our brains to figure out how the world works. This approach is still at the heart of scientific thought today. It's not just about being right all the time. It's about asking questions and trying to find answers. The tension between their incorrect models and their accurate insights is actually a perfect example of how science works. Take the atomic theory and the geocentric model of the universe. One was surprisingly accurate, the other was completely wrong. But both of these ideas drove scientific thought forward. Scientists had to figure out which ideas held up under scrutiny and which ones needed to be tossed out. This process of questioning and testing is what science is all about. So, which of their ideas actually survived the test of time? We've already talked about Democritus and his atomic theory and Aristotle's concept of causality. But there's more. The philosophical inquiries of these ancient Greeks about the nature of reality and existence set the stage for later scientific exploration. They influenced thinkers throughout history, shaping the way we approach scientific questions even today. All right, let's dive into the scientific revolution, a time when questioning the status quo could literally get you in hot water. We're talking about the 16th and 17th centuries, when a bunch of brave thinkers decided to shake things up in a big way. This wasn't just about coming up with new ideas, it was about challenging centuries of beliefs that were backed by some pretty powerful institutions. Imagine living in a world where the church's word was law, and going against it could mean facing some serious consequences. That's the world Galileo Galilei found himself in, when he started supporting this wild idea that the Earth actually orbits the sun. Now, we take this for granted, but back then it was mind-blowing stuff. Galileo wasn't just pushing some abstract theory, he was basically saying, hey, everything you've been told about how the universe works is wrong. And the church wasn't too happy about that. Galileo ended up facing the Inquisition for heresy. Yeah, that's right. The guy we now consider one of the fathers of modern science was put on trial for suggesting that maybe, just maybe, we weren't the center of the universe. It's kind of wild to think about how dangerous it was to be a scientist back then. You weren't just risking your reputation. You were risking your life. But Galileo wasn't the only one shaking things up. We've got Isaac Newton coming in with his laws of motion and universal gravitation. This guy basically looked at the world and said, you know what? I bet I can explain how everything moves, from apples falling from trees to planets orbiting the sun. And the crazy thing is, he actually did it. Newton's laws seem to explain everything from the tiniest particle to the biggest celestial body. It was like he'd cracked the code of the universe. Now, you might be thinking, okay, so they figured out how things move. What's the big deal? Well, it was a pretty big deal. These new ideas weren't just changing how we understood the physical world, they were changing how we thought about reality itself. If everything in the universe follows these mathematical laws, does that mean everything is predetermined? Are we just complex machines following a set program? These are the kind of mind-bending questions that started popping up. And it wasn't just the big names making waves. We've got people like Johannes Kepler, who might not be as famous as Newton or Galileo, but he was doing some seriously cool stuff. Kepler figured out that planets move in elliptical orbits, not perfect circles like everyone thought. This might not sound revolutionary, but it was a huge deal. It was another nail in the coffin of the old way of thinking about the universe. One of the coolest things about the scientific revolution was how it changed the way we do science. These guys weren't just sitting around and thinking really hard, they were observing, experimenting, and coming up with ways to test their ideas. They developed what we now call the scientific method, which is all about gathering evidence and making sure your experiments can be repeated. This was a big shift from just relying on what ancient authorities said. But here's the thing. It wasn't all smooth sailing. As these new ideas started to take hold, they raised some pretty heavy questions. If the universe follows mathematical laws, does that mean everything is predetermined? What about free will? And what happens when we push these laws to their limits? These are the kind of questions that kept scientists up at night and still do, to be honest. The scientific revolution also saw the development of some pretty cool tech. The telescope, for example, allowed astronomers to see things they'd never seen before. Suddenly, they could observe distant planets and stars, and these observations often contradicted what people had believed for centuries. It's like the universe was finally coming into focus, and it was way more complex and beautiful than anyone had imagined. What's really fascinating about this period is the tension between the old ways of thinking and the new scientific ideas. It wasn't just about discovering new facts, it was about fighting for the right to pursue knowledge freely. Scientists were pushing back against centuries of dogma, saying, hey, maybe we should actually look at the evidence instead of just accepting what we've always been told. This struggle for intellectual freedom set the stage for all the scientific advancements that came after. Picture this. It's the early 20th century, and a young patent clerk named Albert Einstein is about to turn physics upside down. We're talking about ideas so mind-bending that they seemed impossible at first. Einstein proposed that time itself could slow down or speed up, depending on how fast you're moving. He suggested that massive objects could bend the fabric of space, affecting the path of light. These concepts were completely counterintuitive, but experiments would eventually prove them right. Einstein's theory of relativity fundamentally changed our understanding of gravity, space, and time. He proposed that gravity isn't actually a force like we thought, but instead, it's a curvature of something called space-time. This idea completely redefined how we see objects interacting in the universe. It's like Einstein took the rulebook of physics and rewrote it from scratch. One of the wildest parts of Einstein's theories is the idea that time isn't constant. We're used to thinking of time as this steady, unchanging thing that ticks away no matter what. But Einstein said, nope, that's not how it works at all. He proposed that time can actually vary depending on how fast an object is moving. This means that time can slow down or speed up relative to the observer's frame of reference. It's a concept that has huge implications for how we understand reality. Now, you might be thinking, that sounds nice in theory, but is there any proof? Well, it turns out there is. Recent experiments have confirmed aspects of relativity, including this weird time dilation thing. Scientists have observed it in high-speed particles and even in the operation of GPS satellites. In fact, these satellites have to account for the effects of both special and general relativity to give us accurate positioning data. So every time you use your phone's GPS, you're actually experiencing the effects of Einstein's theories in action. Einstein also introduced this concept called space-time. Instead of thinking about space and time as separate things, he combined the three dimensions of space with the dimension of time into a single four-dimensional continuum. This framework gives us a more comprehensive understanding of how objects move and interact in the universe. It's like Einstein took our 3D view of the world and added an extra dimension we couldn't see before. One of the coolest predictions of Einstein's equations is that massive objects can bend the fabric of space-time. This bending affects the path of light, which sounds pretty wild when you think about it. Light bending? That doesn't seem right. But scientists have actually observed this happening during solar eclipses, where light from distant stars bends around the sun. It's like the sun is creating a cosmic lens in space. The implications of relativity extend way beyond just theoretical physics. They actually impact our daily lives, especially when it comes to technology. Remember those GPS systems we talked about earlier? They rely on incredibly precise timing, which is affected by the relativistic effects of gravity and motion. If we didn't account for these effects, GPS accuracy would go way off. So every time you use your phone to navigate somewhere, you're basically using Einstein's theories. Einstein's work didn't just change how we understand the universe, it laid the groundwork for pretty much all of modern physics. His theories continue to inspire research and exploration in fields like cosmology and quantum mechanics. It's like Einstein handed scientists a new pair of glasses, and suddenly they could see the universe in a whole new way. But here's where things get really interesting. There's this connection between relativity and quantum mechanics that hints at an even deeper understanding of reality. Both of these theories suggest that our everyday experience of the world around us might just be a limited perspective on a much stranger universe. It's like we're seeing just the tip of the iceberg, and there's this whole weird world beneath the surface that we're only just starting to understand. Remember that weird world beneath the surface we just mentioned? Well, it's time to take a deep dive into it. What if I told you that the very act of observing something could change its behavior? Welcome to the bizarre realm of quantum mechanics, where the rules of our everyday reality simply don't apply. This is a world where particles can exist in multiple states or locations at the same time until they're measured. It's not science fiction, it's quantum mechanics, and it's about to challenge everything you think you know about reality. Let's start with something called superposition. In the quantum world, particles can exist in multiple states simultaneously. It's like if you could be both sitting on your couch and running a marathon at the same time. Sounds crazy, right? But that's just the beginning of the weirdness. There's this famous experiment called the double-slit experiment that really shows how mind-bending quantum mechanics can be. Scientists fire electrons at a barrier with two slits in it. When they're not trying to see which slit the electrons go through, the electrons create an interference pattern on the other side. It's like they're behaving as waves and passing through both slits at once. But here's where it gets really weird. When the scientists try to measure which slit the electrons are going through, the interference pattern disappears. It's like the act of observing the electrons changes their behavior. This is what scientists call the collapse of the wave function. Now, you might be thinking, okay, that's pretty strange, but does it really matter in the real world? Well, it turns out that quantum mechanics isn't just about tiny particles. It has some pretty big implications for our understanding of reality itself. Take neutrinos, for example. These are particles that are nearly massless and barely interact with other matter. They're so elusive that billions of them pass through your body every second without you noticing. But here's the thing. Neutrinos exhibit a phenomenon called neutrino oscillation. As they travel through space, they can change from one type to another. This behavior challenges the standard model of particle physics, which assumes neutrinos should be massless. The fact that neutrinos have mass, even if it's incredibly tiny, contradicts what the standard model predicts. It's like finding out that everything you learned in school about how particles work is incomplete. This discovery suggests that our understanding of particle physics still has some major gaps. But let's go even deeper down the quantum rabbit hole. There's something called the quantum measurement problem, and it raises some pretty mind-bending philosophical questions about the nature of reality. It makes us wonder what it really means to measure a quantum system and whether consciousness might play a role in collapsing the wave function. Some scientists have even suggested that the act of observation creates reality itself. It's the kind of idea that can keep you up at night, pondering the nature of existence. Now, here's where things get really interesting. There's a phenomenon called quantum tunneling, where particles can pass through barriers that they shouldn't be able to cross according to classical physics. It's like if you could walk straight through a solid wall. This effect isn't just a cool party trick. It's actually crucial for processes like nuclear fusion in stars. It's how particles overcome repulsive forces to fuse together and release energy. Without quantum tunneling, stars wouldn't shine and we wouldn't exist. But quantum effects aren't just limited to the world of tiny particles. Scientists have been pushing the boundaries of what we thought was possible in quantum mechanics. They've managed to observe quantum tunneling in larger molecules, suggesting that these weird quantum behaviors might not be confined to the microscopic realm. It's like the line between the quantum world and our everyday reality is starting to blur. The implications of quantum mechanics go way beyond just physics. They're changing how we think about reality itself. The idea that particles can exist in multiple states and that observation can alter their behavior challenges our traditional notions of determinism and causality. It's like the universe is a lot more fluid and interconnected than we ever imagined. Imagine a room filled with the world's brightest physicists, all huddled around whiteboards covered in complex equations and diagrams. They're not just solving any ordinary puzzle. They're on a quest to uncover the ultimate secret of the universe. This is the search for the theory of everything, a single unified theory that could explain all the fundamental forces of nature. It's like trying to find the master key that unlocks every door in the cosmos. Now we've seen how weird things can get at the quantum level, but what if that's just scratching the surface? Picture a universe where particles are actually tiny vibrating strings, and empty space is made of indivisible loops. Welcome to the wild world of unification theories, where the quest to understand everything might change our understanding of anything. The search for a unified theory isn't just about finding elegant equations that look nice on paper. It's about understanding the very fabric of reality itself. We've got these two incredible theories, general relativity and quantum mechanics, that explain so much about our universe. But here's the thing. They don't play well together. It's like trying to fit puzzle pieces from two different sets. They just don't quite match up. This is where things start to get really interesting. Enter string theory, one of the most mind-bending ideas in physics. Instead of picturing particles as tiny points, string theory suggests that everything in the universe is made up of incredibly small, vibrating strings. Each string vibrates at a different frequency, kind of like different notes played on the same instrument. And get this, these strings don't just exist in the three dimensions of space and one of time that we're used to. They need extra dimensions to vibrate in, suggesting that there are hidden layers of reality curled up so tightly that we can't see them. But string theory isn't the only game in town. There's another approach called loop quantum gravity that's equally wild. Instead of focusing on tiny strings, this theory proposes that space itself isn't smooth and continuous like we think. It's actually made up of tiny, indivisible loops, kind of like the pixels on your computer screen. If this turns out to be true, it would completely change how we think about the nature of space and time. Both of these theories are trying to do the same thing: unify all the fundamental forces of nature into one coherent picture. But they're facing some pretty big challenges. For one thing, we haven't been able to experimentally verify either of them. The strings in string theory, if they exist, are way too small for us to detect with our current technology. And the loops in loop quantum gravity are so fundamental to the fabric of space that we're not sure how to test for them either. This is the ultimate prize in physics: finding a theory of everything that can bridge the gap between the huge scales of the universe described by general relativity and the tiny quantum world. It's like trying to build a bridge between two distant islands, but we're not quite sure what materials to use, or even if the islands are in the right place. The implications of a successful unified theory could be absolutely mind-blowing. It could reshape our entire understanding of the universe and reveal hidden connections between things that seem completely unrelated. Imagine suddenly realizing that gravity and quantum mechanics are just two sides of the same coin, or that the birth of the universe and the behavior of subatomic particles are intimately linked. But here's the thing: we're still pretty far from figuring it all out. Scientists are exploring all kinds of avenues, looking for new particles or forces that might provide clues about the fundamental nature of reality. It's like we're detectives trying to solve the biggest mystery in the universe, and every new discovery gives us another piece of the puzzle. What's really exciting is that we don't know where the next breakthrough might come from. Maybe it'll be a new particle discovered in a particle accelerator. Or maybe it'll be some weird observation from a distant galaxy that doesn't fit with our current theories. The key to unification could be something we haven't even considered yet. This search for unification isn't just about physics. It's about pushing the boundaries of human understanding. It's about asking the biggest questions we can imagine and seeing where they lead us. Even if we don't find the ultimate theory of everything, every attempt brings new insights and unexpected connections. It's like climbing a mountain. Even if we don't reach the summit, the view from each new height is breathtaking. We've been exploring some mind-bending concepts in physics, but now we're about to dive into something that might just blow your mind completely. Imagine if you could see your birth, your current self, and your future all at once. That's how some scientists think time really works. It sounds impossible, right? But this radical view of time might actually be the key to unlocking the universe's deepest secrets. The arrow of time is one of those big mysteries that keeps physicists up at night. It's weird because most of the laws of physics don't really care which way time goes. If you watched a video of particles bouncing around, you probably couldn't tell if it was playing forwards or backwards. But in our everyday lives, time definitely seems to have a direction. We remember the past, experience the present, and can't see the future. So, what's going on? This is where a guy named Rudolf Clausius comes in. He introduced this idea called entropy, which is basically a fancy way of measuring how messy things are. Clausius realized that in any closed system, entropy always increases. This became known as the second law of thermodynamics, and it's often linked to why we experience time moving forward. Clausius used a simple example to explain entropy: a cup of coffee. When you pour cream into coffee, you get these cool swirling patterns at first. But eventually, no matter how still you keep the cup, those patterns disappear and you're left with a uniform brown color. This is entropy in action. Things naturally go from ordered, the separate coffee and cream, to disordered, the mixed drink. But here's where it gets really wild. Some physicists, like Julian Barber, think that time might not exist at all. Barber imagines the universe as this timeless landscape where past, present, and future are all just there. It's like looking at a map. All the places exist at once, even though you can only be in one spot at a time. This idea totally messes with our usual way of thinking about time as this straight line from past to future. Now, you might be wondering, if time isn't real, why do we experience it? Well, some scientists think of the universe as this big entropy-generating machine. As the universe expands, new space forms, creating more opportunities for entropy to increase. This increasing entropy could be what gives us the illusion of time passing. But this idea has a problem. If entropy is always increasing, why was the universe in such a low entropy state right after the Big Bang? Some theories suggest our universe might be a lucky accident in a multiverse where most universes start off super messy. The relationship between time and entropy is crucial to understanding the arrow of time. As things get more disordered, higher entropy, that lines up with our sense of time moving forward. But this doesn't explain everything. If you run the clock backwards, you'd see entropy decreasing, things getting more ordered. But we never see that happening in real life. A broken egg doesn't spontaneously reassemble itself, right? The heat death of the universe is another wild concept related to entropy. Eventually, all the stars will burn out, and the universe will reach a state of maximum entropy. At that point, there won't be any usable energy left. The universe will just sit there. In this silent equilibrium, time as we understand it might lose all meaning. These ideas about time and entropy raise some pretty deep questions. If time isn't what we think it is, what does that mean for free will? Can we really make choices if the future already exists? And what about cause and effect? If time is an illusion, how can one thing cause another? Our understanding of time has come a long way. We started with Newton's idea of absolute time, a universal clock ticking away somewhere. Then Einstein came along and showed us that time is relative, depending on how fast you're moving or how close you are to a massive object. Now, we're grappling with quantum theories of time that are even weirder. Just when you thought physics couldn't get any stranger, we're about to venture into a realm where light itself can't escape. At the heart of every galaxy lurks an object so extreme, it breaks the laws of physics as we know them. Black holes are cosmic monsters that push the limits of our understanding, and they might just hold the key to unlocking some of the universe's deepest mysteries. Now, we've been talking about some pretty wild stuff already, but black holes take it to a whole new level. These cosmic giants are so dense and so powerful that they warp the very fabric of space-time. Imagine an object so massive that it creates a point where gravity becomes infinite. That's what we call a singularity, and it's where our current understanding of physics completely falls apart. But here's the thing. We can't actually see what's happening at the singularity. That's because black holes have something called an event horizon. This is like a cosmic point of no return. Once you cross it, there's no going back. Not even light can escape, which is why we call them black holes in the first place. It's like nature's way of saying, sorry, no peeking. Now, you might be thinking, if nothing can escape a black hole, how do we know anything about them? Well, that's where things get really interesting. See, even though we can't directly observe what's happening inside a black hole, we can study their effects on the space around them. And what we've found is pretty mind-blowing. For example, we've recently managed to capture the first ever image of a black hole's event horizon using the Event Horizon Telescope. This was a huge deal in the world of astronomy. It's like finally seeing the monster that's been hiding under your bed all these years. And let me tell you, it's both terrifying and beautiful. But that's just the beginning. Black holes aren't just cosmic vacuum cleaners. They're windows into the deepest mysteries of physics. Take the Event Horizon, for instance. Some scientists think it might be a kind of firewall that destroys all incoming information. Others suggest it could be a hologram, storing information about everything that falls in. It's like the ultimate cosmic hard drive. And then there's Hawking radiation. This was a big idea from Stephen Hawking that suggests black holes aren't actually black at all. They slowly emit radiation over time, which means they can eventually evaporate. But this raises a whole new set of questions. What happens to all the information that fell into the black hole? Does it just disappear? That would break one of the fundamental rules of physics, that information can't be destroyed. This is what we call the black hole information paradox, and it's been giving physicists headaches for decades. It's like trying to solve a puzzle where half the pieces are invisible and the other half keep changing shape. But that's what makes it so exciting. These paradoxes are often where we make our biggest breakthroughs in understanding the universe. Speaking of breakthroughs, there's this idea called the cosmic censorship hypothesis. It was proposed by a brilliant physicist named Roger Penrose. He suggested that every singularity must be hidden behind an event horizon. It's like the universe has a built-in spoiler alert system, preventing the chaos of a singularity from spilling out into the rest of space. Time. But here's where it gets even weirder. Some scientists think there might be such things as naked singularities. Singularities without an event horizon to hide behind. If these exist, it would mean that the universe doesn't always play by the rules we expect. It would be like finding out that sometimes, in some places, 2 plus 2 doesn't equal 4. It would completely change our understanding of reality. Now, you might be wondering, why should I care about all this cosmic weirdness? Well, here's the thing. Black holes might be the key to understanding quantum gravity, the holy grail of physics that would unite our theories of the very big, general relativity, and the very small, quantum mechanics. It's like trying to get your cat and dog to not only get along, but to work together to solve complex math problems. Not easy, but if we could do it, it would change everything. But black holes aren't just important for theoretical physics. They play a crucial role in shaping our universe. Think of them as cosmic recyclers. They destroy old stars, but in doing so, they create the conditions for new stars and galaxies to form. It's like a cosmic circle of life, with black holes at the center of it all. Black holes might be the ultimate cosmic recyclers, but what if our entire universe is just a projection? We're about to dive into a realm where the nature of reality itself is up for debate, and trust me, it's going to challenge everything we think we know about existence. So we've been talking about these massive objects that warp space-time, but now we're going to zoom out even further and look at the very fabric of reality itself. It turns out that some scientists are questioning whether space and time are even fundamental aspects of our universe. This idea, known as emergent space-time, suggests that what we perceive as space and time might actually arise from more basic underlying phenomena. It's like thinking you're looking at a solid object, but when you zoom in really close, you realize it's made up of tiny atoms with mostly empty space between them. But that's not even the wildest idea on the table. There's this thing called the holographic principle that's been making waves in the physics community. Back in 1997, a physicist named Juan Maldacena came up with this mind-bending theory called the AD-CFT correspondence. Now, I know that sounds like a bunch of letters thrown together, but stick with me. This theory basically showed that a universe described by gravitational forces in 3 dimensions could be equivalent to a universe described by quantum mechanics in 2 dimensions. It's like saying that everything we experience in our 3D world could be a projection of information stored on a 2D surface, kind of like how a hologram works. This isn't just some wild speculation either. Scientists are actually working on experimental proposals to test if our reality is holographic. They're looking for tiny fluctuations in space-time that could serve as evidence for this principle. Imagine finding out that our entire universe is basically a giant hologram. It would completely change how we understand, well, everything. And let's not forget about the quantum foam of space-time. This idea suggests that at the tiniest scales, space-time isn't smooth at all. Instead, it's constantly bubbling with virtual particles popping in and out of existence. It's like the fabric of reality is alive with activity at scales so small we can't even begin to imagine them. Now, if all of that wasn't enough to make your head spin, let's talk about the multiverse. Some theories propose that our universe might just be one of many, all floating in some vast, incomprehensible space. It's like imagining that our entire universe, with its billions of galaxies and trillions of stars, is just a single bubble in an infinite ocean of universes. But here's where things get really interesting. Remember how we talked about black holes earlier? Well, they're actually at the center of one of the biggest puzzles in modern physics. Back in 1974, Stephen Hawking made a groundbreaking discovery. He found that black holes actually emit a faint radiation, now known as Hawking radiation. This led to what's called the black hole information paradox. The big question is, what happens to information that falls into a black hole? Does it get destroyed? But that would violate some fundamental principles of quantum mechanics. Or does it somehow escape? But how could it get past the event horizon? This paradox isn't just about black holes. It's actually forcing us to reconsider our understanding of the nature of information itself and how it relates to the fabric of space-time. It's like we've stumbled upon a clue that there's something fundamental about reality that we're still missing. All of these wild ideas, emergent space-time, the holographic principle, quantum foam, the multiverse, they're not just abstract theories. They're attempts to solve real problems and inconsistencies in our current understanding of physics. They're pushing us to think beyond our everyday experiences and imagine a reality that's far stranger and more complex than we ever thought possible. The implications of these theories are huge. They suggest that our understanding of reality is far from complete. There could be deeper layers of existence that are hidden from our current scientific frameworks. It's like we're peeling back layers of an infinite onion, each layer revealing new mysteries and challenging our previous assumptions. We've been exploring the depths of the universe, but now we're going to zoom in on something even more fundamental: our own existence. The anthropic principle is this wild idea that suggests the universe might be fine-tuned just for us. It's like we're living in a cosmic Goldilocks zone, where everything is just right for life to exist. But this raises a mind-bending question. Are we truly special, or just really, really lucky? Let's break this down a bit. The anthropic principle is all about the fundamental constants of nature. These are like the cosmic recipe for our universe, and they're set so precisely that it's kind of mind-blowing. We're talking about things like the strength of gravity, the mass of electrons, and the speed of light. If any of these constants were even slightly different, the universe as we know it wouldn't exist. Stars might never form, atoms could fall apart, and life would be impossible. Now, you might be thinking, wow, that sounds like some serious cosmic planning, and you wouldn't be alone. Some people look at this fine-tuning and see evidence of a cosmic designer or creator. It's like the universe was set up specifically for us to exist. But hold on, because there's another way to look at this that's equally mind-bending. What if our universe is just one of many? This is where the multiverse hypothesis comes in. Imagine billions of universes, each with its own set of physical laws and constants. Most of these universes might be completely inhospitable to life. But in this vast sea of possibilities, there would be a few where the conditions are just right. And guess what? We just happen to be in one of those lucky universes. This idea flips the script on the anthropic principle. Instead of the universe being designed for us, we're simply observing the one universe out of countless others where we can exist. It's like winning the cosmic lottery, but on an unimaginable scale. But here's where it gets really interesting. The anthropic principle and the multiverse hypothesis together suggest that the universe's fine-tuning could be a statistical fluke. It's not that we're special, it's just that in the vast number of universes that might exist, we're bound to find ourselves in one that can support life. After all, we couldn't exist to observe a universe where life is impossible. This brings us to a pretty wild philosophical question. What does all this mean for our place in the cosmos? Are we the result of cosmic design or just a lucky accident in a sea of possibilities? The anthropic principle doesn't give us a clear answer, but it does make us think about the nature of existence in a whole new way. And here's the thing. This isn't just abstract philosophy. Understanding the anthropic principle and its implications can actually change how we see ourselves and our place in the universe. It's a reminder of how incredibly unlikely our existence is, whether you believe in a designed universe or a multiverse. Think about it this way. Every time you look up at the stars, you're seeing the result of these perfectly balanced cosmic constants. The light from those stars traveled millions or billions of years to reach your eyes, and it only exists because the universe is tuned just right. And you, with your complex brain made of atoms that formed in those stars, are able to contemplate all of this. It's pretty mind-blowing when you really think about it. But let's zoom out for a moment and consider what all this means for us on a more personal level. Understanding cosmic complexity and our place in it can actually lead to a sense of inner peace. How? Well, it's all about perspective. When we realize how incredibly unlikely our existence is, whether by design or chance, it can make us appreciate the preciousness of life. Our very ability to ponder these questions is a result of countless cosmic coincidences. It's like we've won the ultimate lottery, and that can be a pretty humbling thought. At the same time, it can be comforting to know that we're part of something so vast and amazing. Whether we're the result of cosmic design or a lucky accident in a multiverse, we're still connected to the entire cosmos. The atoms in our bodies were forged in stars, and we're made of the same stuff as everything else in the universe. We've been exploring the vastness of the universe, but now it's time to consider its ultimate fate. Picture the universe as a massive cosmic clock that's been ticking away for billions of years. But what happens when that clock finally stops? This is the question that keeps cosmologists up at night, and it's not just about distant galaxies, it's about the very meaning of existence itself. Let's start with the big freeze scenario. This is the idea that the universe will just keep expanding forever, growing colder and darker as it goes. Eventually, all the stars will burn out, leaving behind a universe filled with nothing but low-energy photons and a thin mist of particles. It's a pretty bleak picture, but it's one that many scientists think is the most likely outcome based on our current understanding. But that's not the only possibility. There's also the Big Crunch theory, which suggests that gravity might eventually reverse the expansion of the universe. In this scenario, everything starts to collapse back in on itself. Galaxies would crash into each other, stars would collide, and eventually, all matter would be drawn back together into a single point. It's like rewinding the Big Bang, and some scientists think it could even lead to a new universe being born. Now, if those options weren't wild enough for you, there's also the Big Rip theory. This one's really out there. It proposes that dark energy, that mysterious force that's causing the universe to expand faster and faster, might eventually become so powerful that it tears apart everything in the universe. We're talking galaxies, stars, planets, and even atoms being ripped to shreds. It's a pretty intense way for the universe to go out. But wait, there's more. Some scientists have proposed the idea of a cosmic phase transition. This is where the fundamental laws of physics themselves might suddenly change. It's like if water suddenly decided to freeze at a different temperature, except we're talking about the entire universe. This could have some pretty crazy consequences that are hard to even imagine. Of course, all of these theories are based on our current understanding of physics, which might not be complete. Scientists are still trying to figure out the nature of dark energy and dark matter, and how they affect the universe's expansion. Recent observations of distant supernovae have shown that the universe's expansion is accelerating, which supports the idea of dark energy's influence. This acceleration raises some big questions about the ultimate fate of the universe, as it suggests a future where galaxies just keep drifting apart indefinitely. Now, here's where things get really weird. Some scientists have proposed the idea of Boltzmann brains. These are self-aware entities that could theoretically arise from random quantum fluctuations in a cold, empty universe. Imagine a universe where everything has died out, and suddenly, by pure chance, a conscious mind pops into existence for a brief moment. It's a mind-bending concept that challenges our understanding of consciousness and existence in a universe devoid of structure. But let's take a step back and look at the bigger picture. All of these theories about the end of the universe are based on our current understanding of physics. But there's still a lot we don't know. For example, there's something called the vacuum catastrophe, which is a big paradox in modern physics. Basically, our theoretical predictions about vacuum energy are way off from what we actually observe. This huge discrepancy suggests that our understanding of the universe's energy dynamics might be fundamentally flawed, which could have a big impact on our theories about its fate. It's important to remember that these are all just theories. We're trying to predict the fate of something that's billions of years old and incomprehensibly vast. It's like an ant trying to predict the future of an entire city. But that's what makes it so fascinating. Every new discovery, every new observation brings us a little closer to understanding our cosmic home. Just when you thought the universe couldn't get any weirder, we're about to venture into territory that makes our single universe look downright ordinary. What if every decision you've ever made spawned an entirely new universe? It sounds like something out of a sci-fi novel, but it's actually a serious scientific theory that's been gaining traction in recent years. Welcome to the mind-bending world of parallel universes and the multiverse. Let's start with the many worlds interpretation of quantum mechanics. This theory suggests that every possible outcome of a quantum event actually happens, but each in its own separate universe. Imagine flipping a coin. In our universe, it might land on heads, but according to this theory, there's another universe where it landed on tails. Now multiply that by every quantum event that's ever happened, and you get an infinite number of universes, each slightly different from the others. But that's just one way to think about parallel universes. There's also the eternal inflation theory, which is even more wild. This theory proposes that new universes are constantly bubbling into existence, like bubbles in a cosmic pot of boiling water. Each of these universes could have its own unique set of physical laws and constants. In some, gravity might be stronger or weaker. In others, light might travel at different speeds. The possibilities are literally endless. And if that wasn't enough to make your head spin, let's throw string theory into the mix. Some versions of string theory predict an absolutely staggering number of possible universes, around 10,500 different configurations. That's a 1 followed by 500 zeros. To put that in perspective, there are estimated to be only about 10 or 80 atoms in the observable universe. Each of these potential universes could have its own unique set of physical laws and constants. Now, you might be thinking, this all sounds cool, but what does it actually mean for us? Well, that's where things get really interesting. The multiverse hypothesis raises some pretty profound philosophical questions about determinism and free will. If every possible outcome occurs in some universe, does that mean our choices don't really matter? Are we just playing out one of infinite possible scripts? It's a mind-bending concept that challenges our very understanding of reality. If the multiverse theory is correct, our universe might not be unique at all. There could be countless other universes out there, each with its own laws of physics. Some might be similar to ours, while others could be wildly different. Imagine a universe where time runs backwards, or where gravity repels instead of attracts. But before we get too carried away, it's important to note that not everyone in the scientific community is on board with the multiverse idea. Some argue that it's more philosophy than science, because it's incredibly difficult to test. After all, how do you prove the existence of universes that we can't observe or interact with? That being said, some researchers are working on ways to potentially detect evidence of other universes. One idea is to look for signs of collisions between universes in the cosmic background radiation left over from the Big Bang. It's a long shot, but it shows that scientists aren't content to leave the multiverse as just a thought experiment. The concept of the multiverse is fascinating because it pushes the boundaries of our understanding. It forces us to confront the possibility that our universe, as vast and complex as it is, might be just a tiny part of an even grander cosmic structure. It's a humbling thought, but also an exciting one. Who knows what wonders might exist in these other universes? As we zoom out from this mind-bending concept, we find ourselves grappling with the limits of human understanding. The multiverse theory emerges naturally from some of our most advanced models of physics, but it remains highly speculative and challenging to test. It's a reminder that there's still so much we don't know about the nature of reality. Picture a circle of light surrounded by an infinite darkness. This is the realm of human knowledge, constantly expanding but always bounded by the unknown. As we've journeyed through the complexities of theoretical physics, we've encountered mind-bending concepts that challenge our understanding of reality. But now, we're about to explore something even more profound. The idea that there might be fundamental limits to what we can know or understand about the universe. We often think of science as an endless pursuit of knowledge, constantly pushing back the boundaries of the unknown. But what if some of those boundaries are insurmountable? This isn't just about practical limitations like the size of our telescopes or the power of our particle accelerators. We're talking about limits that might be built into the very fabric of reality itself. One of the most famous examples of this is Heisenberg's uncertainty principle. This fundamental concept in quantum mechanics sets a limit on how precisely we can measure certain pairs of properties, like position and momentum. The more accurately we know one property, the less accurately we can know the other. It's not just a matter of having better instruments. It's a fundamental aspect of how the universe works at the quantum level. But the limits of knowledge aren't just confined to the realm of physics. In mathematics, we have Gödel's incompleteness theorems. These mind-bending proofs suggest that within any given mathematical system, there are truths that can never be proven. It's a startling idea that challenges our notion of mathematical certainty and raises questions about the nature of truth itself. Returning to physics, we encounter another potential limit in the form of the holographic principle. This concept suggests that there might be a limit to how much information can be contained in a given volume of space. It's a strange idea that implies our three-dimensional universe might be fundamentally two-dimensional, with our experience of 3D space being an emergent property. This principle raises profound questions about the nature of reality and the limits of what we can know about it. But perhaps the most unsettling possibility is that some aspects of reality might be simply beyond human comprehension. We often assume that with enough time and effort we can understand anything. But what if that's not the case? What if there are truths about the universe that are as incomprehensible to us as quantum mechanics would be to an ant? This idea becomes particularly apparent when we consider quantum mechanics. Despite its incredible success in predicting experimental results, the fundamental nature of quantum reality remains deeply mysterious. The behavior of particles at the quantum level often seems to defy our intuitive understanding of how the world works. Could it be that our brains, evolved to navigate the macroscopic world, are simply not equipped to truly comprehend the quantum realm? As we grapple with these ideas, we're led to a startling possibility. Could the greatest mystery be the limits of mystery itself? Are we capable of understanding the full extent of what we can understand? It's a paradoxical question that pushes us to the very edge of philosophical inquiry. The limits of knowledge in physics raise profound questions about the nature of reality itself. As we explore these boundaries, we confront the possibility that the universe may hold secrets that are forever beyond our grasp. It's a humbling notion, but also an awe-inspiring one. It suggests that no matter how much we learn, there will always be more mysteries to contemplate. This tension between what we can know and what remains unknown is a central theme in the quest for understanding the universe. Each discovery often leads to deeper questions, suggesting that the pursuit of knowledge is an endless journey. It's a reminder that science is not just about finding answers, but about asking better questions. Imagine the universe as a vast symphony, with mathematics as the sheet music. This is how many physicists see reality, and it's a perspective that's both beautiful and mind-bending. We're about to explore the deep and often mysterious connection between mathematics and the physical world. And trust me, it's a journey that'll make you see the universe in a whole new light. Now, here's the thing that's been puzzling scientists and philosophers for centuries. Why should abstract mathematics, something that seems to exist only in our minds, describe the real world so perfectly? It's like the universe itself is speaking to us through numbers and equations. This connection is so profound that it's led some to wonder if mathematics is the fundamental language of reality itself. Let's take Einstein's field equations of general relativity as an example. These equations are often regarded as some of the most beautiful in all of physics. They're not just elegant, they're incredibly powerful, describing how mass and energy warp the very fabric of space-time. It's mind-blowing to think that a set of equations can capture something as complex as the curvature of the universe itself. But it doesn't stop there. We see this mathematical beauty showing up in all sorts of places in physics. Take the Dirac equation, for instance. This mathematical gem didn't just describe existing phenomena, it actually predicted the existence of antimatter before anyone had ever observed it. Imagine that. A mathematical equation telling us about a whole new aspect of reality that we hadn't even discovered yet. It's like mathematics was revealing secrets of the universe that were hidden from our eyes. And then we have symmetries in mathematical equations. These aren't just pretty patterns. They often reveal deep truths about the universe. It's as if the underlying structure of reality is more interconnected than we ever imagined. These symmetries show up everywhere, from the tiniest particles to the largest cosmic structures, hinting at a fundamental unity in the laws that govern our universe. But here's where things get really interesting. There's this ongoing debate among physicists and mathematicians about whether mathematics is discovered or invented. Are we uncovering truths that exist independently of human thought? Or are we creating a complex system that just happens to describe reality really well? Some argue that mathematical truths are out there waiting to be found, like undiscovered continents. Others contend that mathematics is a construct of the human mind, a tool we've developed to make sense of the world around us. This question gets even more fascinating when we consider why the universe seems to follow mathematical rules at all. Is it just a coincidence that we can describe natural phenomena with equations? Or is there something more fundamental going on? It's a question that touches on the very nature of reality itself. Now, here's something to really blow your mind. Some physicists believe that the ultimate theory of physics could be purely mathematical. Imagine a theory so complete, so elegant, that it doesn't even need physical interpretation. It's a tantalizing idea that suggests the deepest truths about our universe might be found in the abstract realm of pure mathematics. But let's bring this back down to Earth for a moment. You might be wondering, what's the most beautiful equation in physics? Well, many would argue that it's Euler's identity, E contours, IP, plus 1 also 0. Now, this might look like a jumble of symbols if you're not into math, but it's actually incredibly profound. This single equation connects 5 fundamental mathematical constants in one elegant expression. It's like the mathematical equivalent of a perfect chord in music, bringing together disparate elements into a harmonious whole. As we zoom out from the abstract beauty of mathematics, we find ourselves contemplating how all of this relates to our everyday lives. It's easy to get lost in the equations and forget that these mathematical descriptions are telling us about the world we live in. The same principles that govern the motion of planets are at work when you throw a ball or ride a bicycle. The quantum mechanics that describes the behavior of subatomic particles also explains why the sun shines and why your computer works. From the mathematical beauty of the universe, we now zoom into a world so small it defies our everyday logic. Imagine a realm where objects can be in 2 places at once, where information travels instantly across vast distances, and where the very act of observation changes reality. This isn't science fiction. It's the foundation of technologies that could reshape our world in ways we can barely imagine. Welcome to the world of quantum technology, where the bizarre rules of quantum mechanics are being harnessed to create revolutionary new tools and capabilities. At the heart of this quantum revolution is the quantum computer. These aren't just faster versions of our current computers. They operate on completely different principles. While classical computers use bits that are either 0 or 1, quantum computers use quantum bits or qubits that can be in multiple states at once. This allows them to perform certain calculations exponentially faster than classical computers. We're talking about solving problems in seconds that would take our best supercomputers thousands of years. One of the most exciting applications of quantum computers is in the field of molecular simulation. Classical computers struggle to model complex molecules accurately, which is a major bottleneck in drug discovery and material science. Quantum computers, however, could simulate these molecules with unprecedented precision. This could lead to breakthroughs in developing new medicines, creating more efficient solar panels, or designing materials with properties we can only dream of today. But quantum technology isn't just about computing. It's also revolutionizing the field of cryptography. Quantum cryptography offers the potential for unbreakable codes, secured by the fundamental laws of physics. This is a game-changer for secure communications. In a world where data breaches and cyber attacks are increasingly common, quantum cryptography could provide a level of security that's theoretically impossible to crack. Another exciting area of quantum technology is in the development of quantum sensors. These ultra-sensitive devices could detect gravitational waves and even dark matter with unprecedented precision. This could open up new avenues for exploration in fundamental physics, potentially answering some of the biggest questions about the nature of our universe. However, it's important to note that quantum technology isn't without its risks. Particularly concerning is the potential impact on current encryption methods. Many of our current cybersecurity measures rely on mathematical problems that are extremely difficult for classical computers to solve. Quantum computers, however, could potentially break these encryption methods, potentially compromising sensitive data and communications. As we look to the future, experts predict that quantum technology will be integrated into various sectors over the next few decades. This could fundamentally alter industries such as finance, healthcare, and cybersecurity. Imagine financial models that can process vast amounts of data to make more accurate predictions, or medical imaging techniques that can detect diseases at an incredibly early stage. The development of quantum technology also raises important ethical considerations. There are concerns about privacy and security, as well as the potential for misuse of powerful quantum computing capabilities. As these technologies advance, it will be crucial to develop robust frameworks for their responsible use and regulation. Perhaps most intriguingly, as quantum technology continues to evolve, it raises profound questions about our understanding of reality and the nature of information itself. The quantum world challenges our intuitive notions of cause and effect, determinism, and even the nature of existence. As we harness these quantum effects for practical applications, we may find ourselves grappling with philosophical questions that have puzzled thinkers for centuries. As we gaze into the vast expanse of the cosmos, a profound question emerges. How do we, as conscious beings, fit into this grand cosmic tapestry? It's a paradox that's both beautiful and terrifying. We're made of star stuff, capable of contemplating the universe that birthed us, yet we're also incredibly small in the grand scheme of things. This cosmic perspective challenges us to find meaning in our existence, even as we confront the mind-bending scale of reality. Philosopher Gottfried Wilhelm Leibniz famously asked, "Why is there something rather than nothing?" This question remains one of the most profound mysteries in modern physics and philosophy. It's a reminder that even as we unravel the secrets of the universe, the most fundamental questions about existence continue to elude us. We've come so far in our understanding of the cosmos, yet we're still grappling with the same existential questions that have puzzled thinkers for centuries. The search for a theory of everything reflects humanity's desire to understand our place in the cosmos and the nature of reality itself. It's like we're trying to peek behind the curtain of the universe, hoping to uncover the underlying rules that govern everything. Physicist Stephen Hawking expressed a deep yearning for this unifying theory, suggesting that it represents the ultimate prize in understanding the universe. He even went so far as to say that it could allow us to know the mind of God. This pursuit of knowledge isn't just about scientific curiosity, it's about our fundamental need to make sense of our existence. But as we contemplate these grand questions, we're also faced with some pretty sobering realities. The concept of the heat death of the universe presents a haunting vision of a future where all stars extinguish, and the cosmos reaches a state of maximum entropy. It's a cold, dark, and silent universe that's hard to imagine. This potential fate of the cosmos raises some pretty heavy questions about the meaning and purpose of existence. If everything ultimately ends in entropy, what's the point of it all? Yet, even in the face of this bleak cosmic forecast, there are ideas that offer a glimmer of hope and wonder. Some scientists propose that consciousness might be woven into the fabric of reality itself. This suggests that every particle could possess a fragment of awareness. It's a mind-bending concept that challenges our understanding of existence and the nature of consciousness. If this idea holds true, it would mean that we're not just observers of the universe, we're an integral part of its very fabric. The implications of modern physics extend far beyond mere scientific inquiry. They touch on philosophical questions about existence, meaning, and the nature of reality, prompting us to reflect on our place in the universe. It's like physics has become a new form of philosophy, using mathematical equations and experimental data to probe the deepest questions of existence. We're using science to explore questions that were once the exclusive domain of philosophers and theologians. It's fascinating to see how different cultures and traditions have incorporated scientific understanding into their worldviews. Many have blended ancient philosophies with modern discoveries to create a more holistic perspective on existence. This fusion of old and new, of science and spirituality, shows how we're constantly trying to make sense of our place in the cosmos. It's a reminder that the quest for understanding is a deeply human endeavor, one that spans cultures and millennia. As we contemplate our cosmic heritage, we're faced with a paradox. Our lives are fleeting on cosmic timescales, yet we can comprehend billions of years of cosmic history. We're incredibly small, yet we're made of atoms forged in the hearts of stars. The universe might seem indifferent to our existence, yet we're the way the universe comes to know itself. These contradictions can be both awe-inspiring and terrifying, challenging us to find meaning in a vast, possibly indifferent universe. But perhaps it's in embracing this cosmic perspective that we can find peace in our place in the universe. By recognizing our connection to the stars and the fundamental forces that shape reality, we can appreciate the wonder of our existence. We're not just passive observers of the cosmos, we're active participants in its ongoing story. Every time we gaze at the stars, we're engaging in a profound act of self-reflection, as the universe contemplates itself through our eyes. As we look up at the stars, we're reminded that our journey through theoretical physics is far from over. Every discovery we make seems to open up new doors, leading to even more profound questions about the nature of our universe. It's like we're constantly peeling back layers of an infinite onion, each one revealing new mysteries to explore. Physicists, like Julian Barber, are pushing the boundaries of our understanding, suggesting that time itself might not even exist. This idea of a timeless universe where everything just is, well, it's mind-bending, to say the least. It's another example of how our quest for knowledge keeps throwing curveballs at us, challenging everything we thought we knew. The arrow of time remains one of those deep mysteries that keeps scientists scratching their heads. We see time moving forward, entropy increasing, but why? And is that really how it works on a cosmic scale? These are the kind of questions that keep physicists up at night, dreaming of new ways to unravel the secrets of the universe. It's a never-ending journey, but that's what makes it so exciting. We keep asking, wondering, and dreaming, because who knows what incredible discoveries are waiting just around the corner.